questions in this field. And so, of course, now that people understand some of the principles here, there's actually thousands of materials which are predicted to be topological. You can look at a database and find these materials. We're starting now to realize that, you know, a lot of the very interesting materials may have magnetism or strong correlations. And so these databases struggle with this because these are materials that go beyond density functional theory. And of course, you know, with this new materials and always coming down, we always have the question, you know, are they topological, and what are the different characterization methods and the signatures of topological physics that's going on? And so we need to develop hand-in-hand experimental and theoretical methods. Of course, one of those relevant for the workshop is the optical and nonlinear responses of these materials. So the Center for the Advancement of Topological Semimetals, or CATS, is a DOE BES Energy Frontier Research Center. And our mission is to understand and discover phenomena in topological materials, in particular topological semimetals, with an eye towards the functionalities that they have in things like spin-based electronics or conventional or quantum computing or sensing. And so you can find out more about the center at our website. And so really, you know, at a high level, what we want to accomplish in the center can be summarized in 3 goals. The first goal is we want to discover new topological materials, in particular magnetic ones. So magnetism gives you a hook where you can control the magnetic state and the topological state with things like applied fields. And so, you know, one thing we want to discover is an ideal magnetic Weil semimetal, which only has 1 pair of Weil nodes, which would then serve as a platform for confirming things like the chiral anomaly in these materials. Another goal is to be able to control a topological material and place it in different topological states through methods like chemical doping or quantum confinement in thin films, or what's relevant to this workshop, maybe applied fields, where we can drive the system into new states. And so, you know, we always search for, you know, very important phenomena, topological phenomena, like the quantum anomalous Hall effect, which of course has a lot of technological ramifications down the road if one were able to find one for a quantum anomalous Hall response, for example, at high temperatures. And the last goal is more in the time domain, where we want to be able to manipulate the response of topological systems using time-dependent fields, so we can switch between topological states, for example. And this is entirely relevant to this workshop. And so, you know, we might use polarized light to switch charge and spin currents in a magnetic topological semimetal, which may have some sensing applications. And so these are sort of the things that we're trying to accomplish. And you can summarize these 3 goals as discover, control, and manipulate topological materials. So the team we put together sort of confronts this complex materials challenge. We have 7 different institutions center. We have efforts to sort of discover and grow new magnetic topological materials in bulk through Paul Canfield's efforts at the Ames Laboratory in Iowa State. We have thin film growth going on at Argonne and UC Santa Barbara. And we also have studies of quantum transport topological van der Waals heterostructures happening at MIT and Harvard. We have various PIs who contribute different advanced characterization tools like STM, ARPUS, high magnetic field magnetotransport, neutron scattering, and optics, and especially ultrafast optics. And of course, you know, we wouldn't be anywhere in this field without people thinking about, you know, what's next in topological materials. On the theoretical sides, we have Anton Burkhoff and Asher and Vishwanath, who were there from the very beginning in sort of charting this path for topological materials. And we also have various other theoretical methods, analytical methods, Monte Carlo simulations, density functional theory, which you know, chart their own path in terms of discovering new phenomena and also help us to understand the experimental data that's coming out of the center. So we've organized the center in 3 thrusts. The first thrust is led by Adam Kaminsky at Ames Laboratory, and this has to do with bulk crystal growth and characterization to find new magnetic materials. Thrust 2 is led by Anand Bhattacharya at Argonne, and this has to do with thin film growth, especially MBE growth of topological semi-metal films. And the last thrust, which is the third thrust, which is probably the most relevant for this workshop, is thrust 3, where we look at how we can manipulate topological states with external fields. And so Dmitry Yarotsky, who's an organizer of this workshop, is the leader of thrust 3. So, you know, one thing that we want to do, or one of the things we want to accomplish in CATS is we want to, you know, sort of be a center for discussion and dialogue in these areas. And so we try to organize different topological workshops where we bring in leaders in the field, we collectively identify where the open questions and research opportunities are. And of course, we establish new collaborations within the center and outside the center. So we've done a couple of these workshops in the last few months, one on manganese bismuth tellurium, which are these antiferromagnetic topological insulators. We did one late in the summer on these manganese 3X topological semi-metal compounds. And then now we have this workshop here. If you're interested in the other workshops, these lectures are posted on our website. So you can go to see the different talks. And look for other workshops in the future. I think we have some other ideas from some of the PIs in the center to do additional workshops. So this particular workshop, and you know, most everybody here has contributed to what we want to try to accomplish in this workshop. But in general, you know, we want to understand nonlinear electromagnetic responses of topological materials and how we can connect those responses to signatures of topological or geometrical properties in these compounds. And so there's a lot of open questions that have been assembled by Dmitry and Chong, and I'm sure some others, which hopefully we'll have some discussion about in the workshop. That's, you know, how do these nonlinear responses emerge from sort of Dirac electrons or Weyl electrons in a semi-metal? What are the nonlinear optical signatures of these topological states? This is a big challenge in our workshop is, you know, ARPIS and STM can see these surface modes, which are sort of great signatures for topological physics, but it's not always possible to prepare a nice surface in some of the more interesting materials. So we need other experimental signatures to sort these things out. What are the role of impurities and scattering in those responses? Oftentimes, you know, we want to tune these materials into a particular state that might involve some chemical doping, or there may be just intrinsic defects in these materials. How do we achieve quantization of nonlinear responses? I'm not even sure what that is. So I'm interested to find out some discussion about that. That would be great. And then, you know, can we actually use these optical responses or nonlinear responses to manipulate these topological states, switch them back and forth, and so forth. So that's kind of my introduction. You know, so I'll just reiterate what the goals are here. You know, we brought everybody together to discuss sort of the forefront work that's going on in this field, and you know, let's talk about what's next. What are the opportunities out there? Let's spend the time now and after the workshop to discuss collaborations. You know, what can we do together to move the field forward? And you know, a very technical one is how do we identify the most viable routes for doing these kinds of experiments, and what are the theoretical underpinnings of understanding these things. And we're really focused in CATS on magnetic materials. So, you know, if we could even talk a little bit about how the magnetism plays a role in these, that would be great. I was also instructed to give a few rules on the workshop. You know, these online workshops are great. We can sort of quickly get people from around the world to contribute these things, but they can be a little chaotic at times. So I would recommend that, of course, everybody stay on mute unless you're speaking. If you are speaking, you know, be ready to go and share your slides during your presentation. Try to stay on time. When you're done, don't forget to unshare your slides so the next person can start. And you know, we want to have an open dialogue. You should feel free to ask a question at any point during a talk. Although sometimes it gets a little awkward with these online formats to do that. So, you know, you can use the raise your hand feature, which is a little button on the bottom, which I think the chair will keep an eye on that and will alert the speaker if there's a question. Or you can just use the group chat. You can type in a question or a thought during as the talk is going on, and then at the end of the talk, the chair will and the speaker can review those questions and start a discussion. So I'm not going to go through this in detail, but you know, the agenda here is split up into 2 days. So we have Dimitri, who will be chairing this morning session. So he will be taking over when my short introduction is done. And then I think Chong will do the afternoon session today. I just want to point out that you know, we do leave time at the end of each day just for an open discussion. And I encourage any of the CATS PIs who are there, even if they're not sort of you know, nonlinear optics people or theory people who are interested in these things, but anybody in the center, you know, should at least participate in those discussions. And so we can get some idea of how we can all work together on this problem. So Dimitri, that's, I guess you got a few minutes left, but are there any questions for me?
Okay, so good morning or good evening, everyone. So I am Ryusuke Matsunaga from the ISSP in the University of Tokyo. So first of all, I'd like to thank organizers for inviting me to this nice workshop. So today I will talk about our recent study of the terahertz nonlinear responses and harmonic generation in topological semimetals. So this project has, so this is our collaborator. So this project has started as a collaboration with Peter Armitage Group in the Johns Hopkins University, and his ex-student Bin Chen has conceived this project. So now he's in the Stanford. Then there are our group members, Kanda-kun and Matsuda-kun has performed the terahertz experiment, and Ikeda-san is responsible for the theoretical part. And Professor Suzanne Stemmer group in the UC Santa Barbara has fabricated the high-quality Dirac semimetal samples. So I deeply appreciate their collaboration. So today I want to talk about the high harmonic generation. The higher harmonic generation has been well studied in the gaseous media for the generation of coherent soft X-ray or UV light source. So it can be utilized for the artificial science or laser ALPS. Then recently, the higher harmonic generation has been also demonstrated in the semiconductor or condensed matter system by using the strong mid-infrared or near-infrared laser light pulse. So it may realize the solid-based compact frequency converter, and also from the fundamental point of view, the non-perturbative nonlinear light matter interaction is also very interesting in the condensed matter physics. Then our group are interested in the lower frequency, much lower frequency around 1 terahertz harmonic generation. So actually, several years ago, we have discovered the terahertz harmonic generation in superconductors, which originates from the resonance with the collective Higgs amplitude mode. Then we discovered the extremely large terahertz nonlinear response in superconductors. So actually, such a large nonlinearity in superconductors has been utilized in application as a sensitive heterodyne detection for the cosmic microwave background radiation. But of course, the superconductor is available only at the cryogenic temperature. So if such an efficient high terahertz high harmonic generation is available at the room temperature, it could be a key technology for the frequency conversion and frequency mixing in high-speed electronics. Then such an efficient terahertz high harmonic generation has been theoretically predicted in the graphene, the two-dimensional Dirac systems. So let's consider what happens if we apply the AC electric field on the electron in the graphene. So the electron is accelerated in momentum space according to the acceleration theorem. Then the important point is the Dirac system has a linear band dispersion. Then The differential of the band dispersion corresponds to the electron velocity, and the electron velocity is proportional to the current. Then, when the electron is accelerated across the Dirac node, the electron velocity suddenly changes its sign. So it means that even if the electric field is a cosine wave, the generated current can be like a square wave. The square wave includes the high harmonic component. So it means that the intraband acceleration of massless Dirac electron can generate a strongly nonlinear current. So it can be a source of higher harmonic generation. So after this theoretical prediction, many experimental researchers have performed a nonlinear terahertz experiment in graphene. But the detection of the terahertz high harmonic generation in graphene was very difficult. So sometimes the difficulty has been explained by the fast carrier scattering in graphene, so which is as fast as 10 femtosecond. So it is much faster than the terahertz field cycle of 1 picosecond. So such an efficient carrier scattering can disturb the ballistic acceleration of electron. Then several years ago, the signature of the terahertz high harmonic generation was first reported by using the 45 stacked monolayer graphene at cryogenic temperature. But at that moment, the data was not so clear. Then 3 years ago, the high harmonic generation in graphene was reported by using the mid-infrared light source with the 63 terahertz frequency in the mid-infrared. So by using such a high frequency pulse, the high harmonic generation can be observed. But in this case, the interband transition becomes very important. So the mechanism is a bit different from the low frequency response. Then very recently, the terahertz high harmonic generation in graphene has been successfully observed in the Nature paper by using the intense light source based on the large accelerator. So this experiment clearly observes the third and the fifth and the seventh harmonic generation in graphene. Then they demonstrated that the nonlinear susceptibility of the graphene is extremely large. So this is several orders of magnitude larger than typical materials. So this is very important experiment. But we consider that there are still some problems left to be resolved. The first problem is the small conversion efficiency in graphene. So please note that the nonlinear susceptibility is very large in graphene. But the total conversion efficiency is determined by the interaction volume. The interaction volume in graphene is limited in its atomic monolayer. So the total conversion efficiency is not so large. So we need a large accelerator to observe the high harmonics. So we need to find another bulk candidate for more efficient frequency conversion. The second problem is the origin of the terahertz high harmonic generation. So in graphene, the carrier scattering is very fast, and the carrier cooling rate is also very fast. So in the Nature paper, they assumed that the electrons were in the quasi-thermal equilibrium with a rapid heating and cooling process within the terahertz field cycles. So they assumed the incoherent thermodynamic model to explain their experimental data. But this thermodynamic model is a totally different mechanism from the original theoretical prediction for the Dirac electron. So we needed to get a deeper understanding into the terahertz high harmonic generation in Dirac system. So in this study, we use the cadmium arsenide thin film samples. So this is a typical three-dimensional Dirac semimetals. So Professor Suzanne Stemmer group has fabricated the high-quality epitaxial thin film samples with the 240 nanometer thickness on gallium arsenide substrate. The Fermi energy shift of this sample is as small as 50 millielectron volts. So this value is smaller than the typical topological semimetals, but please note that it is still much larger than the terahertz photon energy. So the terahertz response in this material is dominated by the intraband response. So actually, this is a terahertz conductivity spectrum. This conductivity spectrum is reproduced by the Drude model. Then we can obtain the scattering time of electron which is as long as 150 femtosecond at room temperature. So this is very long value, such a long scattering time is an important signature of the three-dimensional topological semimetals. Then by using this sample, we performed the nonlinear terahertz transmission spectroscopy. So we generated the quasi-monochromatic terahertz pump pulse with the center frequency of 0.8 terahertz. Then peak field is 31 kilovolt per centimeter in air, then which is reduced to the 6 kilovolt per cent inside the thin film. Then the transmitted pulse is detected in the time domain. So this is a result of the nonlinear terahertz transmission. Then we clearly observe the third harmonic generation signals in the cadmium arsenide thin film. So this figure shows the THG amplitude as a function of the incident field amplitude. The THG is as strong as 100 volt per centimeter. So then it shows clear saturation in the non-perturbative interaction regime. So this THG is very strong and detectable with tabletop light source at room temperature. So in this figure, the fifth harmonic signals is very small, but because of the low detection efficiency in this setup. But in the different experimental condition, we also observe the fifth harmonic generation and in its non-perturbative behavior. Then by using this setup, we also perform the same experiment for graphene. Then we also observe the THG of the graphene. Then we evaluated the nonlinear susceptibility of the graphene. So this is consistent with the previous report in Nature. Then compared to the graphene, so please note that the transmittance of the fundamental wave in cadmium arsenide is much smaller. So this is because the most part of the incident terahertz wave is reflected at the metallic surface of cadmium arsenide. Nevertheless, the generated third harmonics is much stronger in cadmium arsenide. So it means that the much more efficient conversion is realized in cadmium arsenide because of the large volume in this material. Then we also investigate the carrier dynamics by terahertz pump and terahertz probe experiment. So we irradiate the short terahertz pump pulse, then we observe the transient conductivity spectra. So it can be well fitted by the Drude model. Then by using this data, we can obtain the carrier relaxation dynamics. So this is the carrier density as a function of the pump delay time. Then from this data, we can evaluate the relaxation time of the excited carrier, which is as long as 8 picoseconds. So this is consistent with the previous pump probe experiment of this material. This relaxation time of electron is much longer than the terahertz field cycle of 1 picosecond. So it means that the excited electrons do not cool down within the terahertz field cycles. So this is in a stark contrast to the rapid cooling in graphene, which is much faster than the 1 picosecond. So this situation is very different from graphene. So to consider the origin of the terahertz high harmonics, first we consider the incoherent thermodynamic model proposed in the graphene. So in this model, we consider the time-dependent heat transfer from the terahertz pulse to graphene. So it includes the relaxation time. Then we also calculate the heat-dependent scattering time. So scattering time can change as a function of the heat transfer. Then finally, we also calculate the scattering-dependent conductivity spectrum. So this is a response function. So by using this calculation, we can calculate the time-dependent response function and the current waveform. Then we reproduce the thermodynamic model in graphene. Then we also applied it in the case of the cadmium arsenide. So this is the result of the calculation in the thermodynamic model. This THG amplitude as a function of the incident field strength. The calculation shows that the thermodynamic model shows strong saturation. So this is because of the long relaxation time of electron. So because the relaxation time is very long, the heating effect is piled up. So in this case, the THG shows strong saturation, and it cannot reproduce the experimental data. And more importantly, there are more important inconsistency in this thermodynamic model. So this figure shows the dynamics of scattering time in this model. This model shows that the scattering time anomalously increases from the 150 femtosecond to the 1.2 picosecond. So the increase by factor of 8. such an anomalous increase of scattering time is very unrealistic. Actually, in our experiment, we directly observed the change of scattering time in our terahertz pump, terahertz probe experiment. Then we found that the scattering time changes by less than 10%. So it means that the thermodynamic model cannot reproduce the terahertz third harmonic generation in cadmium arsenide. So we should consider the non-thermal kinetics. Oh, sorry. So then we consider the non-thermal microscopic origin of the higher harmonic generation. So it can be classified into the interband current and interband polarization, and the interplay of the interband transition and interband acceleration. The interband current is generated by the acceleration of electron in momentum space, as I introduced first. The second one is the interband polarization. It can be a superposition of the state in valence band and conduction band. Such an interband polarization can emit the light until it dephases, and it can be a dominant for the mid-infrared excitation. But the previous studies of the higher harmonic generation has clarified that if the dephasing of the polarization is much faster than the light field cycles, this contribution is negligibly small. So in the terahertz experiments, the interband polarization is less dominant. And the interplay of even if the polarization dephases, the interband transition can increase the conduction band population, then the electron can be accelerated by the interband acceleration. But in our experiments, the Fermi energy is much larger than the terahertz pump photon energy. So the increase of the electron population by the terahertz pump is not dominant due to the Pauli blocking. So because of these effects, the interband current and acceleration of electron is the most plausible origin for the terahertz high harmonic generation. So we calculated the third harmonic generation by using the acceleration model. So this is very simplified model, assuming the three-dimensional Dirac electron systems and the Boltzmann kinetic equation. Then we can obtain the THG amplitude, and this figure shows the THG amplitude as a function of the incident field strength. So even though this model is very simplified, the calculation reasonably reproduces the experimental data and its saturating behavior within the factor of 2. On the other hand, the thermodynamic model shows strong saturation and unrealistic scattering time. So the interband acceleration can reasonably explain our experimental data. Then by using this model, we also calculated the electron momentum distribution. So this figure shows the snapshot of the electron momentum distribution. So this is in equilibrium, so the electron is around the Dirac node. Then this figure shows the snapshot of the electron distribution at the peak field of the 6 kilovolt per cent terahertz field. The electron distribution is significantly modified in the momentum space. So actually, such a electron momentum distribution and accelerated by terahertz field has been directly observed by the time-resolved ALPS for the surface state in topological insulator. So they clearly directly demonstrated the electron momentum distribution changes in the pump polarization direction, then only for the 2 kilovolt per cent terahertz field. So it is pretty consistent with our experiment. So if we apply a few kilovolt per cent terahertz field for the Dirac electron, the electron is accelerated in momentum space, then it can emit efficient terahertz high harmonics generation. Then we also investigate the subcycle dynamics of Dirac electron under the third harmonic generation. So this is a result of the terahertz pump and the terahertz probe spectroscopy during the pump irradiation. So this is a pump field waveform, and this is a result of the pump probe data. So we can see that the pump probe signals oscillate in time. Then this figure shows the Fourier analysis. Then we can see that pump probe signals oscillate with 1.6 terahertz. This is twice the pump frequency. So we call it the 2F oscillation, and the 2F oscillation is almost equivalent to the third harmonic generation. So this is because now we irradiate the monochromatic terahertz pump pulse, then current appear. So this is the linear current, and this is the nonlinear current. So this second term corresponds to the THG in the transmission of the pump. But this current can be also written like this. So in this case, this term corresponds to the change of the response function. So it can be observed in the pump probe spectroscopy. So in the pump probe signals, there is a 2F oscillation appears. So the important point in this experiment is the 2F oscillation is clearly observed when the probe electric field is polarized parallel to the pump electric field. But if the probe electric field is perpendicular to the pump, the oscillation does not appear. So it means that there is a strong anisotropy in the nonlinear response. So this is an important point. So we can compare this strong anisotropy with the other case of 2F oscillation. So actually, in the experiment in superconductor, we have observed the 2F oscillation in the case of in superconductor. Then in this case, the oscillation is clearly observed, even if the probe electric field is perpendicular to the pump electric field. So it means that the nonlinear response in superconductor is quite isotropic, so because of the S-wave order parameter oscillation in the Higgs mode. Or in other case, if we consider the thermodynamic model proposed in graphene, the effect of the elevated temperature would be usually isotropic. So this situation is very different from the nonlinearity in the Dirac semimetal. But such a nonlinear, anisotropic nonlinear response can be well explained by the intraband acceleration in momentum space. So in this model, the electron distribution changes only along the pump polarization direction, and in other direction, almost nothing happens. So the anisotropy in the nonlinear response is very consistent with the experiment and this model. So finally, we will also discuss the effect of scattering on the acceleration model. In our sample, the scattering time at the room temperature is as long as 150 femtosecond. So this is very long compared to the usual metals, but it's still much shorter than the terahertz field cycle of 1 picosecond. So it means that the scattering happens several times during a field cycles. So one may think that the acceleration model may be invalid in such an efficient scattering case. But we can say no, because the important time scale here is not the field cycle. So please note that the microscopic origin of the current is the unbalanced electron distribution in momentum space. For example, in such a case, there is no current, but if the system is perturbed, the current can flow in this case. So this is an extreme example of the non-perturbative electron distribution. So if the time for building up the unbalanced momentum distribution is faster than the scattering time, the acceleration can generate a large nonlinear current. So we should estimate the time for building up the unbalanced momentum distribution. So by using the acceleration theorem, we estimated the time required for accelerating the electron. So as an extreme example, we consider the time for accelerating electron from the Fermi surface to the Dirac node. So in this case, we obtain the non-perturbative electron distribution. So it can be easily estimated like this. So if the electric field is 6 kilovolt per cent and the Fermi energy is 50 millielectron volt, this time scale is as short as 80 femtosecond. So this is shorter than the scattering time of our samples. So it means that the electron can be accelerated into the non-perturbative momentum distribution before the scattering, even for the low frequency terahertz electric field. So we also calculated the THG amplitude as a function of the scattering time. So it can be classified into the two different regimes. So if the scattering time is faster than 50 femtosecond, so THG amplitude is proportional to the scattering time squared. So in other words, the THG is limited by the scattering. So this is in the perturbative regime. But if the scattering time is longer than 100 femtosecond, the THG is not sensitive to the scattering time. then our sample is here. So this is close to the long tau limit. So so it means that the scattering time of 150 femtosecond is long enough to obtain the non-perturbative terahertz high harmonic generation. So this is our recent result, and very recently we are also interested in the even order nonlinear response in wire semimetals. So previously, for example, by using the near infrared or mid infrared lights, the giant second harmonic generation has been successfully observed in the wire semimetal tantalum arsenide. Or in the transport experiment, the nonlinear Hall effect has been observed in the few layer tungsten ditelluride. It is driven by the very curvature dipole. So this experiment is very interesting, but the terahertz nonlinearity is not so still studied in the wire semimetal with inversion Broncken symmetry. So we are interested in the nonlinear response in wire semimetals. So this is a very preliminary data. So we recently observed the terahertz nonlinear response in tungsten ditelluride with the mechanical exfoliation. Then we observed the second harmonic generation of the tungsten ditelluride at room temperature. Then also we are investigating the crystal axis dependence. Then we observe the strong intraband acceleration signals, so which is much larger than the nonlinear Hall effect, and the other configuration is forbidden by crystal symmetry. So now we are intensively investigating this nonlinear response, and we will show the more detailed data in some conferences. So this is a summary. So we are investigating the terahertz nonlinear response of topological semimetals, which originates from the intraband acceleration of massless Dirac electron. So it may lead to the efficient terahertz frequency conversion at the room temperature. So thank you for your attention.
Okay, yeah, thanks. Yeah, first I want to thank the organizer for the invitation, and I would like to take this opportunity to talk about nonlinear terahertz emission spectroscopy in topological chiral semimetals. Okay, first let me thank my students and collaborators who work on this project. So all of the terahertz emission experiment was done by my student Zhouliang Ni, and the ab initio DFT calculation was done by Yang Zhang, and we have many collaborations with Fernando de Kwang and Adolfo Grushin on this kind of subject. For example, Fernando did develop the KW model for the cobalt silicon work I will talk about, and Adolfo and his student, and Adolfo and his student did many like time binding model calculation, and also we have lots of discussion to understand the data like in many experiments. And linear conductivity measurement was done by Bing Xu in Christian Bernhard group at Freiburg. And we have many also ongoing collaboration with the Pan theory led by like Ken Mali and Rap and their student and postdocs on these projects. And nice samples are from, I would say maybe like mainly like these three groups. So my talk will be mainly focused on the first paper, okay? And I will spend maybe one slide each in the next two papers. So basically the first paper. This is the outline of my talk. In the beginning, I would like to introduce what do I mean by topological nonlinear optics. Then I would like to show you that a nice platform to probe this is the chiral multifold semimetal like cobalt silicon and rhodium silicon. So in the first, I would like to show you the signature for these like multifold fermion by the linear response, which is the optical activity. My main part will be show you the development of the terahertz emission in the mid-infrared region. In other words, below 0.5 eV. Actually, you will see a moment. This is very important to probe these multifold fermions because of any scales. So then I will like show you that the circular photogalvanic effect we observe in cobalt silicon is longitudinal, and also it's purely topological. And yeah, I will show you one slide on the data on rhodium silicon if I have time. Okay, the first part, what do I mean by topological nonlinear optics? So we know topology very well. I mean, start from the quantum Hall effect, then the topological insulators and the wire metals. So usually by topology, I mean, I really mean that quantized, like integer, like a Chen number, for example. And we know how to probe these like quantized, like Chen number, for example, by the quantized Hall conductance in the quantum Hall effect, in the quantum anomalous Hall effect. And also like in terahertz geometry that a few years ago, I worked with Peter Armitage that we observed that quantized terahertz Faraday and co-rotation in topological insulators on the magnetic field. So the nonlinear optics was also pretty, I think, maybe the topic started in the 60s, discovered by Bloomberg. So I mean, we study like second-order generations, and then in the literatures, and lots of study were in the photovoltaic effect, especially in the 80s. So what I'm interested in is whether there's a link between topology and nonlinear optics. Specifically, what I'm interested in is whether we can measure a quantized version of the nonlinear optical response. Okay. So in other words, a nonlinear optical response that's quantized in the unit of the Chen number. So a few years ago, when I was working with Joe Orstein at Berkeley, I mean, we were lucky that we discovered the giant second harmonic generation in tantalum arsenic. And you can see that, so the peak signal of a tantalum arsenic is really it's like 200 times larger than gallium arsenide. So here the gallium arsenide is multiplied by a factor of 100, and 1.5 EV is really sitting on the peak. Then later, I mean, there were also works on photogalvanic effect, which they also report like very large effect. So then a question in the community really came naturally is that whether this large nonlinear optical response is related with the wire nodes. So I would say there were two issues with tantalum arsenic. One is that the Lifshitz energy is quite low. It's lower than 85 millieV according to optical connectivity measurement. So what do I mean by Lifshitz energy is that in the simplest wire semimetals, if you have two quadratic bands, and so this linear crossing is the wire nodes. So this energy scale, like below which the excitation is near the wire node only, I call Lifshitz energy. Above that, you can have like interband excitations from, for example, from wire bands to some high-lying trivial bands. So that's issue, because in the previous measurement, like including ours, actually the photon energy is much larger. I mean, here is in a better scenario, but it's still larger than the Lifshitz energy. The second issue is that in tantalum arsenic, there are like trivial electron pockets and hole pockets. So the Fermi surface is a little bit complicated. So to summarize, in experiment, and I think it's not really clear to say that whether the large nonlinearity is like solely related with the wire nodes. Even though the theory paper by Yang Zhang and Nagosa and Binghai, they argue that if two of the three bands are wire bands, the contribution dominate. So I mean, most likely the contribution is still dominated by these bands related with wire points, but it's not really kind of obvious in experiment. So then that's motivated to identify new materials with only topological bands at the Fermi energy, which is a multifold semimetal, which I will show you in a moment. Secondly, maybe more importantly, there is a fundamental reason that second generation and the linear photogalvanic effect are not related with a Chen number, okay? So in the 80s, it was developed by Van Boltz and Friedkin and Sturman that they show that the linear photogalvanic effect is related with gauge invariant quantity called shift vector. And recently, I mean, we also show, and also the speaker tomorrow, Morimoto also show that the second generation can also be related with a shift vector. So in other words, like the second generation and the linear photogalvanic effect are related with its geometric quantity instead of barrier curvature. When as a shift vector, I really mean that you shine light, then the electron cloud have a shift in the real space. That kind of contribute to second generation and the linear photogalvanic effect. Perhaps the first example, or the first nice example that relate with nonlinear optics and topology is this quantized circular photogalvanic effect proposed by Fernando de Kwam and in the Joe Morse group in 2017. So the idea is that, so different from tantalum arsenic has mirror symmetry. So the wire points with opposite Chen number are at the same energy. However, if you break mirror symmetry, the wire points with opposite Chen number are at different energy. So imagine that if the chemical potential is sitting here and you can shine like a low frequency light, For example, low frequency circular polarized light, like left circular polarized light, it only excites near the left wire cone, but it's poly-blocked in the right wire cone. So in other words, basically light is only probed one of the wire cone. So even though they come in pairs, but this is poly-blocked. So by this way, actually you can measure the charge of one cone, okay? So then, yeah, so unfortunately, chiral wire semimetal does not exist in nature, even though maybe actually two materials were predicted. Then later, a few group, maybe two group, they predict that the multifold semimetals, which means that the degeneracy is not 2, either 3 or 4 with higher numbers. And also they are chiral materials, like they might be better system to realize the quantized CPG. So for example, like in these multifold semimetal, like rhodium silicon, so the idea is still the same. You polyblock one of them, they measure, then excite maybe in the left cone. So what they calculate is this DJ over DT. Sometimes people call this CPGE effect or the injection current. And the response function is this could be beta ij. So what's quantized is the trace. So basically, if you sum over the beta xx, beta yy, and beta zz, in the linear model, the trace is quantized in the unit of Chen number times the fundamental constant. So you can see that in the rhodium silicon, so in tiny binding model work, so they predict that below 0.7 EV, I mean the response is more or less kind of quantized. Okay, so and I also want to emphasize, like in rhodium silicon and in cobalt silicon, actually they're cubic. So all of the traces are the same. We need to measure one of them. We just need to multiply 3, then we can measure the total beta. So now let me introduce what do I mean by chiral multifold fermions and their signature in optical conductivity. And I will show you the example of cobalt silicon, even though we also did rhodium silicon. But due to the time limit, I will only focus on cobalt silicon. So cobalt silicon and rhodium silicon crystallize in the famous crystal structure called B20, like a structure. I mean, you might heard of like skyrmions in like iron germanium or manganese silicide. They basically have the same structure, like chiral structure. So they can have left-handed and right-handed. And if you look at the 111 axis, you can see there are threefold rotation symmetry. And if you look at the cobalt silicon from the top, they wind in one way, but the silicon atom wind in a different way. And under the photo emission show that at the gamma point, I mean, they show that there's a threefold fermion here, and at R point, there is a double wire. Because of the spectral coupling in this material is like 20 millieV, so RPUS was not able to see the splitting. I mean, in theory, so if we include that, the threefold fermion will split into into a twofold wire and a fourfold spin 3/2. A double wire will split into a twofold chiral pairs and a sixfold spin 1. So because the energy scale is very low, so we did optics conductivity measurement, which is so basically we measured longitudinal conductivity on the linear response. A few things I want to say here, I mean, due to the time limit. First is that, this is the total data is the blue. So you can see very sharp Joule response. It turned out this sharp Joule response is from this high mobility electron pocket at the wild point. So at the gamma point, it's a very heavy hole. So it doesn't really contribute to like low frequency transport. So if we study the temperature dependence of the spectral weight of this Joule peak, and we can extract the Fermi velocity, and it turned out the experimental value agree with the DFT value very well, within 4%. So the Joule response is really from this double wire electron pocket. The other thing, you can see that there are a few like sharp phonons. So then if we subtract the data with the Joule response and the phonon, so what's left is the interband response, which is this red, okay? So you can see there are two like quasi linear regime. One is up to 0.2 EV, another above 0.2 EV, it has a different slope. So then we did some like ab initio calculation and also tight binding model. We show that, the kink at 0.2 EV is related with the different interband excitation. So below 0.2, the excitation is only at the gamma point, the threefold. Then below 0.2, the R point, the polyblocked. Then above that, it's also allowed. So that's why there are two quasi linear regime. So I didn't have the kind of time to show you a plot, but in this paper, we show that below 100 millieV, so the data is better to be explained if you can include the spinor coupling. In other words, in the optical connectivity, you can show that actually the fourfold spin 3/2 quasar particle here do exist. But the main message here is that if you want to see the signature of multi-fold fermions, actually we really need to below like maybe 0.5 eV, because about 0.6 eV, this saddle point will be activated. Okay, so that's why we developed terahertz emission spectroscopy in the mid-infrared region, which was not really done in the past. Okay, so before talking about kind of mid-infrared terahertz emission on these materials, I would like to talk about the longitudinal circular photogalvanic effect versus transverse. So when I say longitudinal circular photogalvanic effect, I mean that let's say if you shine a circular polar light normal incident to the sample, and the current flows along the wave vector in the sample. So this is called longitudinal CPG. In contrast, if the current flows perpendicular to the wave vector, this is called a transverse CPG. So the transverse is the most common one. It was observed in many materials like tantalum arsenic, for example, and like TMDCs, for example. But the longitudinal CPG was first observed in 1979 in chirotoluene, but it was not really observed until it was not really observed in the second or third compound until the past 2 years. Okay. So then the cool thing about the longitudinal CPG is that if you shine left circular polar light, actually you can pump charge out of the sample. So this is the case when you shine like a DC, when you shine continuous wave laser, so you can have a DC current. But if I shine a pulse, you can have a transient current. So this is what actually we are studying. And we of course, we study other geometries so that this transient current pulse can emit terahertz to the free space under off-normal incidence. So here is the more common way that you see to measure photogalvanic effect, like in many materials. So there are a few things that one need to be careful with. Of course, one can kind of overcome this, but the first thing is the contact. So you need to align on crystal axis, and if second thing that if the laser spot is not in the center, you can have a thermal gradient, you can have thermal current. The third thing is that so if the laser spot is smaller than sample, you can have like drift current, or actually it's really a diffusion problem. In other words, the current you measure is not really the true response under like J equal to maybe eta EE. Okay. As I said, if you're careful enough, you can deal with this. But my group was not used to study this. So we decided to use a different route so that we don't need to worry about these three problems. So this is what we do. So this is a kind of a different way to measure photogalvanic effect is that we shine pulse on the sample of normal incidence. So there is a surface current component which will emit terahertz. So we are not the first group to do terahertz emission. There were a few works in the literature to study this phenomenon already, but what's new here is that we pushed into the mid-infrared regime. Okay, so the terahertz pulse is related with the dJdt. As you can see that in the beginning, I show you the theory. So what's the quantized quantity is also dJdt. So that's also one of our motivation. And the energy scale of terahertz is like 4 millieV and like 50 Kelvin. So generally, we can use a second-hand generation to align the sample very nicely, but it turns out in this case, that doesn't really matter because it's a cubic and it also has 3-fold rotation symmetry on the 1-1 surface. So for the CPG, actually, it's isotropic. Now let me show you the data on the cobalt silicon. So first, I mean, how do we know it's a longitudinal CPG instead of transverse? So we did like polarization dependence by changing the quarter wave plate of the pump, and also we measure the terahertz emission out of the incident plane and in the incident plane. So this yellow plane in the incident plane. So first, let's look at the terahertz pulse measure that is perpendicular to the incident plane, which is the yellow. So you can see that on the left, so we can basically rotate the quarter wave plate to change the polarization from linear, circular, and with opposite helicity, you can see that on the left and right circular. So the signal is actually the same. If you look at the time trace, it's even more obvious, so they're the same. And the definition of the CPG is really the difference between left and right. You can see it's almost 0. And the sum is actually LPG. So basically, CPG is not allowed in the direction that is perpendicular to the incident plane. However, when we measure the terahertz electric field in the incident plane, you can see that on the left and right circular power right, they change sign. If you look at the time trace, you can see that they really flip. The CPG is the yellow and LPG is the green. So basically, the CPG is really dominating. So we are measuring in the time domains, and so how can we compare with our data with theory? So here, we can also like derive a similar version of the kind of Joule transport in the linear response to a second order response. So here is a current, J is equal to here, I call this quantity eta, okay? I call this quantity eta to compare with the sigma usually you see in the linear response. So J is equal to eta EE, this is second order conductivity. So what we do here is that we measure in the time domain, then we do a Fourier transform in the frequency domain. So what we get is terahertz, it's very small. So I use a big omega here. And for the incident photon energy, I use a little omega. So what happens here is that the incident pulse is a pulse, it has a field, it has different energy. So let's imagine that you can take like 2 energy and then take the difference, okay? So then the difference is a big omega, is a terahertz frequency. So you can see that when we measure the second order conductivity as a function of terahertz frequency, for example, at 0.25 incident photon energy. So this is really a pulse. This is centered at 0.25. And different frequency generation is basically the data here. You can see it's more or less frequency independent, okay? So then we are actually in the regime that the hot electron time, sorry, one difference between the transport, the Joule transport and the second order conductivity, that the tau here is the hot electron lifetime instead of like Joule transport lifetime. So we are actually in this regime, the hot electron lifetime is much smaller than the one of the terahertz frequency. So actually what we are measuring is actually J is equal to beta X times tau E squared. So there is a different regime that the hot electron lifetime is very long. This is kind of in the quantized regime. So we are not in the quantized regime yet because tau is too small. So then what we do next is that at this 0.25 EV, so we measure the second order conductivity, then we take an average, then we can plot a data point here. And of course, we can change incident photon energy from 0.2 EV to like 1.1 EV, then we can measure spectrum. A few things here is that the peak is very high. It's like 500 microamp per volt square. So this is very large, actually. I think it's the largest among any like chiral crystals. Second thing is that, as I said, so we are measuring beta XX times tau, okay? So then, so density functional theory can calculate the spectrum of the beta XX if we have a chemical potential. Then here we use a simple like constant tau assumption. Then tau becomes a free parameter. So then we tune the curve. We basically multiply beta XX that is from DFT, then times the tau. So we match the width. So we match the width and the peak to constrain the value of the tau. So then we can extract the tau, then we can extract the beta XX. So beta is basically 3 times beta XX is like 3.3. So it's not quantized. And as we already know, we're not in that regime. The second message is very important is that at this peak, it's a giant peak. So we did a momentum resolve contribution. So you can see that it's only contribute from the gamma point with 3-fold and R point, which is the double wire. It doesn't really have any contribution from the end point, which is settle point. So basically this giant peak is purely topological because at the Fermi energy, we only have multifold fermions. And this is also consistent with our earlier linear conductivity. Okay, I need to wrap up. So how do we see quantization and why is it not quantized? So it turns out, I mean, these materials are compensated semimetals. So basically we have like hole pocket and electron pocket. In other words, the chemical potential cut flat bands. So this is important because, so this red curve is the same red curve I show you this slide. So you can see that if we go to lower energy, actually there is a sign change, okay? So then how do you realize quantization? So if the chemical potential is here, then we can see that quantization is really happening at low energy and it's very narrow. However, if we put the chemical potential above flat band, the quantization window will become much larger, still at the low temperature. So then about this sign change, I mean, Fernando Tequan and his student used a very simple model, the K.B model with the quadratic correction. So why do they introduce quadratic correction is because this flat band is not true flat band, but it's really bent down, okay? So in this simple model, because of time limit, I just would like to tell you that, so the contribution of the threefold fermion, the gamma point is this green curve. So it has like plateau window, then kind of disappear. So then for the double while, they use a simplest model. Simplest model is really a step function of 4. So the total sum is that quantize the negative and sign change and become like a non-quantized plateau that we saw, which is 3.3. So the cool thing is that there's a sign change when the chemical cut flat bands. This was clearly observed in rhodium silicon because the energy splitting between the threefold fermions and double wire is much larger than the cobalt silicon. So actually this sign change was pushed above like 0.2 eV. So actually we can observe in experiments. So this is really the longitudinal CPG we observed in rhodium silicon. I mean, you can see really kind of drastically different from the theory prediction earlier. So so what's happening here? So it turned out that in the early theory, when they did the time binding calculation, so they put the chemical potential above flat band. So that's why it has this like nice plateau-like feature. We can also reproduce in the DFT calculation. I mean, I just put it upside down. So you can see that if we put the chemical potential above the flat bands, I mean, it's more or less kind of agree with earlier study, except that the quantization window is less nicer than the cobalt silicon because here the spectral coupling is much larger. It actually spoils the quantization. I mean, there are other. So rhodium silicon was really widely studied in the literature. You can see there are 2 more studies. So let me summarize. So anyway, the role of the chemical potential is really a key. So actually it cut the flat band and then it leads to these kind of a rich feature. And so far it's not quantized yet in both material, but in cobalt silicon, we show that it's purely topological origin and it's very large. Yeah, I want to thank for your attention.
Thank you so much to the organizers for the introduction or for the invitation to come and speak about some of our work today. So today I'll mainly be focusing on this aspect that we measured that was photocurrent driven transient symmetry breaking in tantalum arsenide. And to do so, I'll provide a background first on the directionality and types of photocurrents that are excited in tantalum arsenide, specifically on this 112 phase that we probe, and then how it is that we can use these photocurrents to control the degree of symmetry breaking in this material. So this work was very much done in collaboration. Specifically, we're at Los Alamos National Lab, and we've benefited from great collaboration with CATS, including Dimitri, Shanshen, and then especially for this work, recognizing work with Peter Worth that was done, who helped us really kind of understand what it is that's happening. So we'll start, I mean, very briefly with just sort of this outline of why topological semimetals and what is very appealing. This audience certainly needs no introductions, but when you look at these materials, specifically looking at them from either a fundamental science perspective of broadening the classification of topological materials beyond the insulators to these gapless semimetals, but also from the point of view of a lot of technical applications, there is a tremendous amount of appeal specifically with tuning symmetries in order to induce topological phase transitions, making them suitable, for example, in topological transistors. And so when you take these 3D analogs of graphene, these Dirac semimetals, and you break either time reversal inversion symmetry to generate these Weil semimetals, you now have sources and sinks of Berry curvature that results in really interesting experimental manifestations that sort of Rob had talked about before. These can be especially seen from the ARPAS in terms of Fermi arc surface states from magnetotransport and looking at this charge bumping between the 2 Weil nodes and the chiral anomaly. And then there's this kind of question of what is the maybe the imprint or the topological signature in optical probes. And early on, you looked at cases of linear optical probes, looking for signatures of the chiral anomaly due to, say, the step-like feature in the optical conductivity, and then the subsequent linear scaling. Very early, as was sort of introduced before, there was a lot of interesting work on the nonlinear optical response. And there is this question as to whether the nonlinear optical response can encode specific topological properties or specific topological characteristics. And so this was sort of seen in the case of the transition metal mononucleotide families that we were studying here in our present study, tantalum arsenide, of having this really giant nonlinear response. And the fundamental characteristic of this transition metal mononucleotides is the presence of this broken inversion symmetry. And so when you look at the dominant contribution of the photocurrent that's attributed to broken inversion symmetry, it's the shift current response. And so you can sort of think of the shift current as a shift in charge density within sort of the Wegener-Zeit cell, where you can have this added contribution due to sort of topologically non-trivial characteristics. So the other effect was looking at non-trivial topology manifesting in the form of the injection photocurrents. And so this is, these are asymmetric excitations of your carriers in accordance with CP selection rules. And so here, this work that was done before, this work here, it was looking at sort of the directionality of the net photocurrent and attributing this directionality to the specific chirality of the wild nodes. So there was additional work that was done out of Ken Birch's group, also looking at these photocurrents under static excitation in the mid-IR, and you ended up sort of seeing on a given tantalum arsenide face a lot of possibilities of the possible photocurrent excitations, be it shift current excitations, injection current excitations. So getting a sort of clear picture of how to excite specific photocurrents and where these photocurrents are flowing, and how it is that we can necessarily characterize these photocurrents not just under mid-IR, but even sort of optical excitation, was sort of a question that we asked. And the way that we did this was similar to what was already discussed, is rather than focusing on CW photocurrents, we focused on these ultra-fast photocurrents in the form of terahertz emission. So the experiment is quite simple. We just use an optical pulse of 40 femtoseconds, normally incident onto a 112 face of tantalum arsenide, where we can control the helicity of the pulse with a quarter wave plate, or control polarization of the pulse with half wave plate. Optical excitation on the tantalum arsenide generates a photocurrent, and this photocurrent will emit a terahertz proportional to the change in the current, and then we just detect this through standard electro-optic detection techniques. So in our study, we predominantly focused on tantalum arsenide, but we also had measured other members of the transition metal mononucleotide family, niobium arsenide, for example. And what we sort of looked at were two main crystal faces. One was the 001 plane, which contains mirror planes in AB, and then the other was this 112, which has this projection on the C-axis, where this is the direction of broken inversion symmetry. So you can identify this clearly on our crystal. We define our orthogonal on the 112 face. We define two high symmetry axes on this crystal, of being the 1 - 1 0 and 1 1 - 1. And these are verified with second harmonic generation. So we are confident of our alignment. So what did we see? One of the first experiments we did was a helicity dependent experiment. And so here we varied the helicity of the optical pump pulse and we looked at the polarity reversal of the emitted terahertz that occurs under this. So we looked explicitly at this 1, 1, minus 1, or 1, minus 1, 0 phase, which is contained entirely within sort of that AB plane. And as we tune the helicity from left circular polarization through linear polarization to right circular polarization, we see a clear helicity reversal. It's 180 degrees. We didn't really see any variation in the frequency content, and the change in amplitude that we saw from the emitted terahertz was proportional to the degree of ellipticity. And so you can actually see this as we plot peak-to-peak terahertz intensities as a function of quarter wave plate angle, that as we tune from linear to circular, we get a dominant contribution that is attributed to changing of that pump helicity. So rather than sort of the previous works, which were really focused on mid-IR excitations, here under optical excitation, we wanted to make sure that we can clearly understand what it is that this photocurrent was originating from, what was the microscopic mechanism. And so we sort of considered three possibilities. One was this idea of this circular photogalvanic effect through these injection photocurrents, but then there was also this effect of a circular photon drag effect, which could be attributed to the, in part, the generation of a current due to the photon momentum imparting a certain degree of momentum. And then a spin galvanic effect, which is sort of an asymmetric scattering due to your spin carriers. And so you can actually distinguish between a circular photogalvanic effect and a circular photon drag effect very cleanly under symmetry considerations. And then because we measured a terahertz emission, we can gain dynamical information on the transient photocurrent. And we should be able to distinguish then from a slower spin flip scattering process of a spin galvanic effect by the bandwidth of that emitted terahertz pulse. So first, we looked at sort of the symmetry contributions. And so when we looked at this helicity dependent photocurrent on the 112 phase along the 1, minus 1, 0 axis, we can see that as we rotate through 180 degrees, we see a nice change in polarity. So photocurrents are directional. On the 001 phase, you see a really large quench of the emitted terahertz, specifically at near normal incidence. And a helicity dependent terahertz signal only arises again as you start to become more grazing here at 45 degrees. And so what we're sort of seeing is that same sort of empirical relations seen from static photocurrent measurements of the excitation of transverse photocurrents under helicity excitation. This is not entirely surprising when you go and you actually work out what is symmetry allowed under this photocurrent excitation. So if you look at the generation of the photocurrent and you separate it into its two contributions of either photogalvanic or a photon drag effect, and under helicity dependent excitations, you only consider like the antisymmetric tensor component, then you get a form of the either circular photogalvanic or circular photon drag that looks like this. And under the symmetry constraints of a C4V or 4mm symmetry, we only sort of have these non-zero elements that are contributing. And so at normal incidence on the 112 phase, when you look along the specific 1, minus 1, 0 axis where we observe helicity dependent photocurrents, we find that the circular photogalvanic effect is symmetry allowed, but the circular photon drag effect is symmetry forbidden. And so based on this, we can really clearly distinguish that the photocurrents we were exciting under helicity dependent excitation in that AB plane we can rule out circular photon drag effect and find supporting information, supporting case for circular photogalvanic. Now, this question of the spin galvanic effect was addressed through looking at the terahertz bandwidth. So in this case, when we measured with electro-optic sampling, what we always sort of found is that the emitted bandwidth was limited by our detection crystal, which was zinc telluride. So in order to sort of get at what the true emission bandwidth was, we performed a different type of experiment, which is known as terahertz field-induced second harmonic generation. And the way that this experiment works is that you, due to the presence of the electric field, you measure from your second harmonic response the terahertz field. And the advantage of this is that by pulling out the terahertz field from that second harmonic in a T-fish experiment, you don't have a bandwidth limitation that's imposed by sort of the vibrational resonances of your detection crystals. And so you can measure this sort of in free space just purely by how the terahertz field is imprinted on the second harmonic. And when we did this, what we found is that this was a very broad emission bandwidth on the order of 10 terahertz, which itself is limited by our time resolution in our experiment. So this sort of implies a sub 100 femtosecond temporal dynamic of this helicity dependent photocurrent. And that kind of fast time scale is really more consistent with the type of momentum scattering you would see from an injection current versus sort of that slower spin scattering that you would see from a spin galvanic effect. So we sort of now have identified that under optical excitation along this specific 1 - 1 0 axis, we will always generate a injection photocurrent, and that can be attributed to a circular photogalvanic effect. Now, when we looked along that 1 - 1 axis that contains a projection along the c-axis, we see something quite different. In this case, we see virtually no polarization dependence as we tune wave plate from either left to right circular polarization or as we tune from the linear polarization. So dominantly polarization independent response. Additionally, you see that this photocurrent is also highly directional, and it's highly directional along this axis that has that projection of broken inversion symmetry. And as compared to that broad emission spectrum that was measured from the helicity dependent photocurrent, you see an intensity power spectrum along the c-axis that is significantly reduced, significantly narrow. And so this intensity power spectrum is shifted towards this lower frequencies of around 1 terahertz. So all this sort of points to a fundamentally different mechanism for photocurrent generation along this axis it's strongly linked to this broken inversion symmetry. And as I'll show you later, is that we can really attribute this to shift current generation and then exploit the polarization dependence, not along this axis, but polarization independence along the other axis, 1 - 1 0, to control symmetry breaking. So as part of the technological appeal of these topological semi-metals is that they sort of sit at this phase boundary between these strong and weak topological insulating states. And so what's sort of really exciting from the viewpoint of ultra-fast spectroscopy is that by manipulating specific symmetries, you open up this possibility of tuning between distinct topological phases. And this has sort of been looked at in various either theories or in experiments where you're using these ultra-fast light pulses to realize high symmetry electronic or crystalline switches. And so this has sort of been theoretically proposed as using light pulses to transiently break symmetries through Floquet states. In the case of tungsten ditelluride, there is this aspect of a photoinduced shear distortion, reducing symmetry or restoring centrosymmetric symmetry in tungsten ditelluride, annihilating Weil nodes. And then, as will kind of be discussed later in this workshop, there's this idea of excitation of the symmetry breaking phonons. And so either choice of electronic or crystalline symmetries to manipulate these Weil states would be a really powerful way of inducing these topological type transitions. But one of the things that we kind of noticed is that the photocurrent, the generation of a photocurrent by itself will naturally break spatial and time reversal symmetry. So we performed a type of experiment that was a time resolved second harmonic experiment. And so what we did was we sent in at normal incidence a optical pump pulse, the same optical pump pulse that we used before on the same 112 phase to generate these photocurrents either along the 1-1,0 or 1-1-1 axes. And so we can control the polarization of that pump pulse to either being circularly polarized or linearly polarized. So we know that we can excite specific photocurrents along one direction or the other. And then we came in with another optical probe pulse that was tuned from 800 nanometers to then into the deeper infrared, and measured the second harmonic patterns that were generated. And so what is shown here is a time sequence from prior to pump excitation to the moment of pump excitation, and then times after pump excitation. And in the case of prior to pump excitation, we get SHG patterns that are all well described by what was previously found in literature, and everything is captured by that 4mm1 prime, or what is essentially what is the C4V symmetry plus time reversal symmetry. But as soon as this pump pulse impinges on our 112 phase, what we sort of notice is that you get this dramatic reduction on the specific 1-1-1 channel of the SHG signal. And then you see these two photoinduced lobes that emerge. And if just by inspection of the data alone, there is sort of an absence of a mirror symmetry from the pattern. So while here we're mirror symmetric around 180, we sort of have indication that maybe there's something, a symmetry that is being lifted here due to this removal of this mirror symmetry. In addition, if you look very, very closely at this pattern, you actually see that under pump excitation, there's a rotation in the pattern that is also transient. And like these photoinduced lobes, it lasts along the same time scale. So the rotation in the pattern, as well as the presence of these photoinduced asymmetric lobes, are intimately linked to whatever the same sort of symmetry breaking transition is occurring in the second harmonic. So when we sort of investigated this, we looked at the specific time traces. And so here from the SHG pattern, we're just looking at what the dynamics of that photoinduced feature are. And we have these two time traces under either linearly or circularly polarized excitation. And in all cases, that time scale is really quite fast. And so the emergence of these asymmetric photoinduced lobes is on the order of a picosecond. And so this sort of points to something that is electronic in origin. We don't really see any temperature dependence in the decay time. You see a very weak fluence dependence. And you also see a dependence on pump helicity, but it's only really present on extremely short timescales. It's on the order of the pulse duration. So to really sort of rule out any sort of symmetry, any structural transition, we took our crystal to the LCLS and we performed time resolve X-ray diffraction experiments. So setting up in the same configuration, the same experimental geometry as we had in our time resolve second harmonic experiment, we looked at specific Bragg peaks in the on the 112 face, and so we were here is shown the 103 Bragg peak, but we also looked at 200 Bragg peak, and we measured either the presence of or absence of certain Bragg peaks under photoexcitation, under that same optical photoexcitation. And what we really saw was very trivial lattice dynamics, and particularly the Bragg peak itself just showed a characteristic sort of drop of intensity that can be attributed to Debye-Waller factors. And then there was evidence of an acoustic strain that a shear wave, for example, or sorry, yes, it was a longitudinal and shear wave that was generated because of that unique geometry of the 112 face. But again, these were timescales much longer than that timescale that was associated with the emergence of that symmetry breaking photoinduced feature we probed from second harmonic. So we think that we are in fact seeing something that is really electronic in origin. So with the help from Peter Orth from Ames Lab, we looked at how to assign the symmetry and the specific symmetries that were broken in this photoexcited state. So we started from the bulk symmetry of that 4 mm 1 prime and described and are able to fit the patterns nicely as sort of previously reported in literature. And then we considered what are the possibilities that could be occurring. So one possibility is that photoexcitation generates a bunch of carriers that quenches the bulk second harmonic, and you're left with a second harmonic that is both contribution of surface and bulk. So in this case, though, the surface second harmonic is sort of indistinguishable from the bulk second harmonic. Both will have the same sort of symmetry. In this geometry, both will have the same sort of pattern. And this is because of this presence of this diagonal mirror. So in order for us to really describe our data, we had to lift this diagonal mirror. And when we do so, we're left with what is the lowest symmetry state of this one symmetry state. And not only did we have to lift the diagonal mirror, we also had to break time reversal symmetry to account for both the asymmetry in the lobes as well as rotation in the pattern. So it's that breaking. Okay, it's that breaking of diagonal mirror symmetry and time reversal symmetry. And this is a condition that is satisfied by a photocurrent on the 112 face. So the other point to bring up is that when we change our probe energy from either 800 nanometers to 1200 nanometers to 1400 nanometers, the generation of the photoexcited carriers alone found to be an insufficient condition for transient symmetry breaking. So we really needed to resonantly probe these states responsible for generating the photocurrent. And the last thing is that we can exploit the symmetry of the shift current to control the degree of symmetry breaking we observe in second harmonic. So from the two high symmetry axis on the 112 face, the 1 -1 axis is proportional to intensity. So you find no polarization dependence. But a shift current along 1 -1 0 can be controlled by polarization. And you can either turn it on or off by having your polarization aligned along either of the two high symmetry axes. So if we look at this sort of model, we have two photocurrents that we excite under linear excitation, one along 1, 1, minus 1, the other along 1, minus 1, 0. And having symmetry allowed photocurrents along 1, minus 1, 0 results in a net photocurrent that will break the diagonal mirror. And you can see this, for example, from our Territz emission, where as we tune our pump helicity, we see that polarization dependence from tuning linear pump pollution along 1, minus 1, 0. And this is exactly seen in our SHG data as we, as the pump helicity, or sorry, as the pump polarization is tuned and shift currents become symmetry allowed, you start to see that rotation in the pattern becomes more prominent, and then the asymmetry in those photoinduced lobes starts to emerge. So in conclusion, we have ultra-fast helicity-dependent photocurrents generated within the AB plane. They're attributed to circular photogalvanic effect. We have these polarization-independent photocurrents along the C-axis attributed to shift currents. And then this transient symmetry breaking observed in our time-resolved SHG, we're attributing to the presence of a shift current along the 1, minus 1, 0 axis, which we can control through the symmetry constraints on the photocurrents. All right, thank you so much for your time.
Okay, so thank you very much for a nice introduction. I first like to thank Rob, Dimitri, and Tune to organize this very nice workshop. I'm particularly delighted to talk here because I really feel a strong sense of the community. So following the three very nice talks, I'd like to continue the discussion, especially to give our perspective on nonlinear Terahertz control in topological materials. So this work is done in my group at Ames Lab and Iowa State University. And the fundings are mostly from Department of Energy. So first, I'd like to talk about the driven quantum coherence and some control concepts. So for example, periodic driven of electronic coherence and phononic coherence, right? So this allows to actually control the symmetry at sub-cycle time scales. And this can distinguish some very exotic topological phenomena. In the rest of my talk, I'd like to discuss some recent examples. So for example, we can think about light-induced Dirac or wire semimetals by exciting phonons, coherent phonons of selective symmetry, the Raman symmetries or IR symmetries, so the infrared symmetries, right? So, and those has a strong consequence of the photocurrent transport. So then I will give a summary and outlook of my talk. So before moving on, I'd like to just comment that terahertz and phonons of topological properties are heavily covered of this workshop. So I just quickly glimpsing the program, and I will partially some talks. I'm very interested to continue to hear this exciting progress and also some other topics of this workshop. So first, let's talk about the light-driven quantum coherence, right? So one frontiers of the condensed physics is to do a rational design of the quantum matter, especially by driven coherence. So there are many exciting progress. So it's hard to list all the things here. I'd like to give a limited view from my group. So this work from my group, right? So for example, we can think about to use the light to control the supercurrent, right? To use light to induce current. So the oscillating current as a driven coherence, right? So in this case, it can steer the quantum system to steer the quantum evolution. So for example, here, the idea is not to use electrodes, but use this light to accelerate these electrons and shift from a surface, as we have heard, right? So, and then so this allows to dynamically to control the symmetry. So during the subcycle of the pulse, right? And this allows to see some exotic phenomena. So for example, in the case of electronic like systems, so you can think about, so this can create a new state of matter or to detect the hidden states of the collective modes. So for example, Higgs mode, as we heard from first speakers, right? So here you can think about to create two Higgs modes at two different energies of this iron-based semimetals, right? And then you can see a high harmonics on terahertz up to fifth harmonics and things like this. So, and this are rather generic concept, as you know. So the light can coherent control of the magnetic order. So a couple years ago, so we wrote this paper to show that the quantum coherence can actually to drive spin bonding and the Canting orders. Right? So in this talk, so the idea is to extend this concept to use a driven coherence to control the topological matter, right? Especially by driven phonon coherence. So why do we use this phonon coherence? Because the periodic driving of the lattice can selectively to control the symmetry. So we have the IR phonons, the infrared phonons, or the Raman phonons, right? So this has a different symmetry. So we have this a periodic oscillation, right? So this can actually to lock to electronic system by the electron phonon coupling, and this can coherent to modulate the topological properties. So to demonstrate this concept, so we actually to first to see some symbol systems. So for example, we can use a IR or Raman symmetries to control the collective modes in the semiconductors, right? So for example, you have this perovskite semiconductors. So in the case of this rush of excitons, right? So you have this spin splitted band. So all this band are coupled selectively to the IR or the Raman symmetry. So you shine the light, you see the quantum oscillations from the phonon coherence, right? All the coherence, either by Raman or IR, they couple to the different bands. So they shift the band differently. Right? So you can use this to control ferromagnetic polarons or the Rydberg exciton. So this concept seems very solid. So I'd like to skip these details, but just to mention for the sake of sparkling the collaboration. So this is a part of the big efforts of the AIMS-Lab FWP. So this is like a national lab multi-PI project. So in this case, my role here, so besides the science, is we are developing this advanced coherent spectroscopy and microscopy tools. So for example, very relevant here is, so we can use the terahertz to couple to a scanning probe microscopy to do this near field terahertz microscopies. So this can be used to study the photocurrent and conductivity at the terahertz and nanometer scales, right? So this could be very interesting for the people if you like to collaborate. So we're very interested, right? So, and then, so let's really talk about control the topology by coherent phonons, right? So there are at least two strategic advantages for coherent phonons. Number one is periodic driving of the lattice vibration to actually to give you a dynamic stability, right? So this seems to be a paradoxical concept. So how this type of modulation can give you a stability. But as you know, this is a coherent back and forth motion. So this has quantum memory, right? So as we shown before, so actually, if you're really exciting this coherent phonons, so for example, in this business selenide, you can reinforce the coherent protected quantum transport on the surface by cutting the scattering from the surface to the bulk. So for example, you shine the light, then you see these coherent oscillations of phonons, right? So these phonons can elong the transport lifetime on the surface, right? So I like to keep this part short because our workshop is on the semimetals, right? But just to comment that, so you can tune the surface transport by phonons or by pump photon energy, right? So this terahertz pumping is very relevant to excite this topological surface state, right? So as shown in this paper. But now, so let's focus on the second part. So the second advantage for a coherent phonon control is this periodic driving of the system of different symmetries, IR or Raman. It actually give you a way to do a topological switching at very fast time scales. So as we've shown here, so basically, if you excite the Raman phonons, you keep the symmetry. So you preserve the inversion of Thomasson symmetry. In this case, you can do a transition from a strong TI to a weak TI, so with a direct tornado phase in between, right? So, but then if you to selectively to excite infrared photons, so this can break inversion symmetry or time resource symmetry. In this case, you can actually drive phase transition from a directional metal to a bidirectional metals, right? So to do this full phase topological control. So I like to focus on these two examples along these two orthogonal axes to the rest of my talks. So let's start from here. So basically, it's indeed true that if you're just shaking or twisting of the lattice, you can actually drive this topological phase transition at very fast speed, so at terahertz speed. So these are very compelling for device concepts. So for example, as we heard, these topological transistors are nearly dissipation-less electronics or even quantum computation. Let's start from here. So how to do this light-induced topological phase transition, right? So the tool here is called the terahertz nonlinear spectroscopy. So in this way, you shine 2 terahertz pulses, right? So there are 2 pulses, right? And then you measure the nonlinear response. So this is a third order nonlinearities from this excitation. So there are 2 contributions. On one hand, it's called the pump-probe contributions, right? So this is basically, you can think about this as a time-dependent response function, right? The dissipation as the conductivity or the dielectric constant of the inductivity, right? So here, think about this just like a ultra-fast multimeters, right? So basically, there's no contact, you just shine pulse, and then you drive the time dependence of the response function. And the second response is called the four-way mixing, FWM contributions, right? So this is to measure the coherent responses, right? So all the measuring theories have been shown in our prior papers. I like to just keep it short. So the key point is that this type of spectroscopy have become highly relevant because of the amazing development of the laser pulses. So now in a tabletop, so this is some example on my lab. So basically, you can tune laser pulses from the fine infrared, the mid infrared, or the visible range, right? So like from 1,000 micrometer, 100 micrometer to 10 micrometer. So this becomes very relevant. So basically, in this talk, I like to focus on this terahertz region. You can generate the single cycle terahertz pulses with almost a megavolt per centimeter on the free space, right? So, and then so you can so this is some raw data of terahertz 2D spectroscopy. You can really just see many of the interesting responses. But now the question is, how do we do a topological switching from a strong TI to weak TI and with a direct metal in between, right? So by this periodic driving of the Raman phonon coherence. So this experiment is done in a 3D direct materials, the zirconium pentachloride. So this materials has some specific properties. So for example, electronic state shows a very small electron and hole pockets, right? So, and then so you have this highly linear dispersion, right? So a very high energy, and also this has a band inversion, which are very sensitive to atomic spacing of the layers, right? So in this case, you can think about, so to drive the interlayer spacing between certain axes, right? To control the band inversion, right? In this case, let's take a look at this mode, A1G mode. So this is a Raman symmetry. In this case, so a preserved inversion centers, however, you modulate the spacing between the B axes. This is very, this actually can control the band conversion, the band inversion, right? So this is the idea. So before us, you can actually already change the volume by quasi-equilibrium like tuning, right? You can change the temperature of string to control the volume, right? So here, as shown here, so by tuning the temperature, you can actually reduce band gap, right? And then so you modulate band gap from 30 milliV to almost 0, right? And then you open it again, right? So also this can be done by string also. So the electronic state driven by coherent Raman coherence is very different from this equilibrium tuning, because number one is, so this type of tuning is slow, right? It costs a lot of energy. And also you only access to certain lattice motion, right? So you cannot, so for example, you cannot break inversion symmetry, right? So because all this are normally uniaxial strings and things like this, right? So you can only control symmetry, but for the coherent phonon pumping, so you can actually to access different symmetries, either the Raman or infrared, or you can have access to a large of the phase space. Right? So let's see if we can really do this terahertz light-driven Raman coherent oscillation. So if we shine the light, then we see a pronounced coherent oscillations, right, after this terahertz pumping, right, especially in this high field. Right? So then we can do a Fourier transform of this coherent beating signals. Then we go to the frequency domain, right? So then you see that there's a consistent of the peak from this coherent beatings to the static Raman signals, which is taken our sample in same position, right? So, and then you see that, so this confirms that you can actually use light to coherent driven this the Raman oscillation, right? So now the question is, what is the electronic state that are driven by this the Raman coherent, right? So before doing the experiment, we asked like Lin in the CAT center to give us some ideas how this electronic state evolve as function of the displacement of this A1G, like this Raman phonon, right? As you can see here, so if I have this different distortion of the phonons, you see this band gap actually changes, right? As function of the oscillations, right? The band gap can actually close down, right? As function of the phonon oscillations and this phonon amplitude. And also, as you can see here, so this band inversion, so this is the projection of the telluride p orbitals, right? So you can see here, so this band inversion is actually also changes. You actually go from a strong TI to a weak TI with a Dirac-Semimetal like phase in between at the critical point, right? So now the question is, can we really see this type of topological phase transition in this Raman coherent dry state, right? How to do this? So now we can measure the differential terahertz transmission as function of time delay, right? So now we see that clearly there's a evidence of to build up this metastable state, right? So here is the terahertz part, right? Coming in, it's about 736 kilo per centimeter. Then we see a coherent oscillation from phonons, but exclusively during the coherent oscillation, you see this build up of the state, right? After the coherent oscillation is gone, then you have a metastable phase. So one of the questions, what is this phase, right? Can we underpin the topological features of this phase, right? So as you can see here, so actually we have many pieces of the evidence. Number one is how to prove this phase is a topological non-trivial, right? So basically, so the signals has a strong temperature dependence, right? So the signal only builds up when you have a barrier curvature dominate of the transport measurement. Like for example, this anomalous Hall effect. Right? So above that, so everything's gone, right? So there's no signals. Number two is if you see this E-field dependence, there's a strong photo excitation threshold. The signal is nothing, is absent below the threshold. Above that, you see a huge increase of signals. It's much larger than the E-field needed to drive this thermal topological phase transition, right? So, and then so also you can have a evidence from the relaxation time, right? So we can measure the decay of this metastable state, right? So here is actually the decay time is prolonged at exactly this Dirac-Semimetal state. It means when you have the relaxation from the weak TI to the Dirac-Semimetal state, is so decay time is prolonged. So this is a critical, because basically this is a very similar to graphenes when you have this type of Dirac state, right? So the lifetime is prolonged here. So, and then like many other evidence also, I mean, like for example, you can take a spectra to see a non-thermal feature. So these are really different from the thermal tuning. It's not just the temperature, right? So the spectra is totally different. So let me skip this part. So let me focus on a second side of like phonons. As we know that if we can break the unit symmetry or temperature symmetry of the system, we can actually dynamic generate this wire points by light, right? So now we can think about this as a light-induced phononic symmetry switch, right? So if we can not only to excite the Raman symmetry, if I if we can excite certain phonons of the IR symmetries, right, then we could be able to have this light-induced the Weyl point. Right? So unlike this A1G mode, right? So in this case, we have this switch. So these are not switch, right? So basically, the emission centers is preserved by this motion, right? So now, if I simply to drive a different mode, it's called B1U mode, as you can see here, right? If I just drive this carrier motion, right? So you see this carrier motions of the cage. So effectively, they give you a emission symmetry breaking along the C-axis, right? So along the C-axis. So in this case, you actually remove the emission centers. So this gives you the opportunity to see the effect of this Weyl band like formation, right? So this is the ideas of this, right? So this will have a, so if we can use light to selectively to excite this IR phonons, then this allows to have a strong consequence of the system. Number one is you can actually generate a huge nonlinear photocurrent, even in this central symmetric crystal. So zirconium-205 is a central symmetric crystal. In principle, you should not have any nonlinear optical response at Chi2 level. Right? So this is the thing. But if you can break symmetries, then you can have a huge Chi2 nonlinear photocurrent. Right? So we have heard some very nice accounts about how to generate this current, right? So I will skip this part. So, and the second part is, so if you have a light-induced symmetry switch, then this can dynamically generate a Weyl point, right? By twisting the lattice, right? So then this can strongly affect the transport properties, right? So for example, as we know that if we have a Dirac materials, right? So there's no CPG because essentially it's imposed by selection rules, right? However, if you have this Weyl Semimetals, as we heard, so this can have a very strong circular photogalvanic effect. This means that the light helicity can be transferred to the bands, this Weyl band with definite chirality, right? So the question is, you can use circular pulse light to couple of the Weyl nodes. Of course, we know that there are many details and so there are many reasons for this, right? So we have to prove that the carriers are really from this the lowest conical state, right? You can excite these phonons, right, to break symmetry, and then you need to show that such photocurrent has a strong correlation with the chirality of the band, right? So next, I will give some evidence we can actually answer all these questions, right? So we have heard a very nice talk about how to do this tariffs for the current emission, and also how to do a pump probe, right? This output pump tariffs probe. I will just skip this part, but only just to point out, right? By photoexcitation, we can excite the charge carriers between this telluride phonons, this dimer state, this zigzag state, right? So, and then you have this a local surge of the E field, which we hope that to see the coherent phonons, right? So this is the idea. So, but now the first question is, can you really to generate this infrared phonons with broken emergent symmetry, right? So is that possible? So first, let's take a look of the linear response, right? Indeed, so here we just shine the terahertz light, right? It's a very simple measurement. Now you see there's 3 phonon mode, right? So the dominant one is this 0.7 terahertz, which is from this B1U phonon. This phonon is exactly what we need to break the emergent symmetry here. Right? So can we excite such phonons by pulse, right? So the question is yes, right? So after pulse, you see there's a strong, so this is by optic pump and terahertz probe, we see this strong oscillations are long-lived, right, after the pulse. Right? So if we just to get this oscillatory component, then we see that there's a mode, exactly this like B1U mode. So this B1U mode is going to remove the emergent centers. The hope is so this can give you a light-induced Weyl point, right? So now the question is, how do we see this? So, and one thing to show is so we have to prove that such phonon are indeed to break the emergent symmetry to generate this huge giant photocurrent along this dynamically symmetry breaking axis, which are not which is forbidden in the ground state, right? Because this zirconium pentatetraphile is a standard symmetric crystal, as we know. Indeed, so right after this excitation, when we see phonons, you see this huge oscillations, right? So these terrace emissions are from photocurrent, right? So basically you see that, so this photocurrent is along the c-axis, which is from this broken symmetry axis, right? So it's very good. And then you can rotate samples just to convince yourself this are really from c-axis and not from the transient E field, right? Just from the part. So it's very good. This means now you can actually induce a broken invariant symmetry by the phonons, right? By this coherent phonons. Now, after that, so right, you can convince yourself once you have this emergent symmetry breaking by this B1U phonons, you can actually have a wire points, right, splitted, right, in this DFT calculations. You dynamically generate a two pair of the wire points, right, in the AB plane, right? So, and then you can see that only the A-axis has the band tilting, right? It means that if this is true, we should see a huge, reasonable CPG effect along this A-axis, but not along this C-axis, right? So that's exactly what we do, right? So basically, you can just to measure this circular photogalvanic effect, right, as a function of the polarization angles, right? You see that along the A-axis, there's a very different photocurrent if you're exciting with a right and left surface polarized light, right? So, and then if you increase temperature, so now become very small, and also this is almost gone. However, so, and then this A-axis CPG is much larger than the C-axis. So this is the, if you see the C-axis, if you see this C-axis from empty circles, right, this are small, basically, right? So, and then, so also along the C-axis, there's no temperature dependence. It means probably this some sort of the residual effect, right? So the bottom line is, so now we have a light-induced CPG effect only along the A-axis, right, of this. So, but now the question is also how to prove that this photocurrent amplitude has a correlation with the band topology, right? So here we did this anomalous Hall effect. So basically, to use this to identify this Barry curvature temperature, right? Below 160 Kelvin, there's a buildup of this Barry curvature that dominate anomalous Hall effect. So here, if you look at this photocurrent, right? So you see here, so about 160, there's almost negligible of increase, but now below 160, so you have a huge jump of this photocurrent, right? And also, so it's so this are definitely there when the Barry curvature is dominant, right? So number one, so in this, it's very interesting how this correlation between this light-induced coherent B1U phonon-driven state to this magnetic field-driven state. Because in the magnetic field, you break temperature symmetries, then you have this anomalous Hall channels, right? So basically, so in this coherent-driven state, we actually see a very similar behaviors, right? So it's also a very interesting to see that this photocurrent is actually from the lowest conical point, because essentially, so you can identify a temperature. So basically, it's called the Lipschitz transition. It means now the Fermi surface are cutting through this conical point exactly at this temperature. So now you see this photocurrent actually goes down, right, on this temperature, because you have a particle and the Hall reversal, right? So there's a sign change of the carriers. So that's why all these are fully consistent. It means that this photocurrent are really from the lowest band of this conical point, right? So, and all this to make us believe that this provide a compelling evidence. There's a direct wire phase transition, even to drive a coherent B1U phonons without application of static of electrical or magnetic field. So let me just quickly, I just have like one slide, right? So I think I'm out of time, but I just have one slide. So basically, we know that this CPG can happen in the Western metals, but it can happen in many other materials, right? It's not necessary to be the proof. So it's more important to see that how this type of a band can relatively change the quantum transport, right? So if you look here, so by this type of a time result terrace emission, you can actually measure this, the scattering rate, right? So as you can see here, if you decrease this temperature, So then there's a strong sharpening of the width, right? So as we described in our paper, you can actually divide the detect response functions to get the true photocurrent spectra. So this is the AC photocurrent, right? So as you can see here, the width is clearly narrower from the high temperature to low temperature, right? So basically, this is the clearly a coherent transport with a vanishing scattering because you have the spec, right? So if you look at the width of this, so this is the scattering rate, right? As function of temperature, you see that about the Barry curvature temperature, you have a long scattering time, but now the scattering rate quick goes down right at the Barry curvature run, and then you go to low temperature with a nearly like vanishing scattering, right? So this means that you have a very very long of the lifetime of this current, right? So if you put in the Fermi velocity and this current of this very long transport lifetime, you can actually get a 10 micron of the ballistic like mean free path. So this is very big, right? So, and also from this temperature correlation, so we believe so this exceptionally robust quantum transport can be explained by this carrier protection. Let me just quickly summarize of this, right? So I don't have time to talk about the more recent works. So basically, we can show that you can actually to image this photocurrent at terahertz and nanometer scales, and we are like pushing hard to this 2D tera spectroscopy and things. So let me just simply acknowledge that so this experiment is done in my group, especially so Liang is the person who did this terahertz IR phonon pumping, right? And Chirag and did this Raman phonon pumping, and so terahertz scanning near field optical microscopy are done by Richard and Cheng Kun, and so this work benefits from a strong collaborations with many people. So we have Bo-Chun Song, who did most of the theory at AIM side, and so Lilin did from CAS Center, like did this like work on the DFT and like many things, and so Peter also chipped in, and so the samples are from the Lee and so Goose group at the Brookhaven National Lab, and also from Fadina's group at Notre Dame. So thank you very much for your listening.
So today in this talk, I'll present about how optical responses are related to the Riemannian geometry of quantum states. This work was done in collaboration with Guangyu Guo, Dr. Nagosa, and Ashwin Vishwanath. Okay, so geometry of quantum states often appear in electromagnetic responses. The most well-known is the Berry phase. It has the geometric meaning of the solid angle in the space of quantum states, as is well known, and this can be expressed as the flux integral of the Berry curvature. And this Berry curvature is important in the understanding of the anomalous Hall effect, and more recently, in the anomalous non-linear Hall effects discovered by Sotman and Fu. And it is also responsible for other quantized phenomena in topological materials. Another important geometric concept is the quantum distance. It is the measure of geodesic angle in the space of quantum states. And its infinitesimal form is what is called the quantum metric or quantum metric tensor. This quantity hasn't been much studied as the Berry curvature, but recently it is getting more attention than before because of its relevance to anomalous superfluid rate and orbital magnetism, especially in flat band systems, including twisted bilayer graphene. And it is also responsible for other DC responses to inhomogeneous electric fields and so on. One of the common threads in geometric responses is that they are properties of complex Riemannian geometry, And this is natural because wave functions are complex valued objects. So we need a theory of complex geometry. And in this sense, the quantum metric and the Berry curvature can be unified as a one complex value quantity called the quantum geometric tensor. And this is the most common and fundamental quantity in the study of quantum geometry. And this defines the metric or distance in the manifold of complex manifold of quantum states. And another important common thread in geometric responses is that they are interband hybridization effects. So geometric responses appear as quantum corrections to classical intraband effects. In this, okay, so given that these geometry responses are interband effects, the resonant optical processes are expected to be wonderful for exploring quantum geometry because they are inherently quantum mechanical and interband effects. And indeed, recently, the quantum geometry of optical responses has been an active topic of study, and there are many studies recently. But these previous studies relating quantum geometry to optical responses had limitations like no straightforward quantitative relationship between the two, or unclear geometric meaning, or when it applies so well, it was limited to effective two-band systems, such as the vicinity of the band crossing points in semimetals. And all these aspects reflects the fact that there's no proper geometric description of optical responses. The main challenge is that optical responses are not explained by the geometric property of a single state. For comparison, let us consider the DC response. Here by DC response, I mean the response to static electromagnetic field. In this response, in metal, the single band, metallic band in metal, and the single ground state in insulator is related to the response. So their geometric property, only the geometry of the single state is related to the response. Because this concept is well established, there is no conceptual issue. But on the other hand, optical responses pick a pair of states, particular pair of states whose energy difference matches the photon energy. So for a well-defined description of geometric property in this optical process, we need a theory of geometry of a pair of states here, M and N. But there's no such theory up to date. So the main goal of this work is to construct such a theory of geometry of a pair of states. So to introduce the main idea of this work, let's first remark on the importance of the transition dipole moment in optical processes. The fundamental interaction between electron and light is described by the electric dipole moment, dipole interaction like this. And this is equivalent to introducing the minimal coupling through the vector potential. And there are two different gauge choices. So I'll take this view. So in this view, because the interaction Hamiltonian is the dipole Hamiltonian, if we perturbatively expand to define the nonlinear conductivity tensors, this optical conductivity tensor is a function of dipole moment matrix element and the band energy difference. So all information of the quantum state is encoded in the transition dipole moment. So this transition dipole moment contains all information on quantum geometry. So, okay, so our central idea is that this transition dipole moment can be regarded as a tangent vector on a manifold. So in differential geometry, the tangent basis vector associated with the momentum coordinate ki is written in an abstract way as a differential operator dki. This is a mathematical description. So in the quantum mechanics, because the position operator is this differential operator, it can be, it is expected to be some tangent vector on a manifold, on some manifold. And I will show that this idea really works, and I'll show that the transition dipole moment is in fact the tangent vector on the manifold of self-periodic flow states. So, and with this concept, all other geometric properties are derived naturally. So in the following slides, I will construct the Riemannian geometry of quantum states relevant for the optical processes in 3 steps. First, I define tangent vectors as I described. And second, I will define the inner product of 2 tangent vectors living at the same point. And then I define the parallel transport of tangent vectors. And this process completely defines the Riemannian geometry. And okay, after this construction, I'll show that this is really powerful by showing that by finding the manifestation of the Riemannian curvature tensor, which hasn't been studied before. And I will use this shorthand notation for the momentum derivative in the following. Okay, so to show that the transition dipole moment is a tangent vector, let us revisit the meaning of the position operator and rethink about it. So the position operator in the flow state basis is written like this. This is a classical band theory result. And this the off-diagonal part is conventionally viewed as the Berry connection. So by this term Berry connection, it means that we view it as a geometric quantity connection. But here, I will view this same quantity in a different perspective. For that, I will rewrite this Berry connection in this form. So here you are, this is just the self-periodic below wave function. So this is position. And I introduce n, a finite number n, as the number of all bands. So this should be infinite, but yeah, and temporarily I take this as finite, and in the end, I'll take this to be infinite. And also, I'll take this n also be the number of position eigenstates within the unit cell. So if I do this, this self-periodic flow state becomes the n by n unitary matrix. Okay, with this construction, the Berry connection can be written like this: U inverse dU. And this is what mathematicians call Bauer-Cartan form. And form, or a more current form of the unitary matrices, and it has one-to-one correspondence with the tangent vector on the manifold of unitary matrices, because they're related by the multiplication by U, which is invertible. So, okay, we are almost to the point. So, and then the manifold of physical self-periodic flow state is given by modeling out the U1 pH degrees of freedom. And this is done by substituting this operator to the covariant derivative. And then this, this is the sum of our different MN indices, and EMN is the specific matrix element of the position operator, for the state MN. So our key observation now is that this tangent vector lives on the n square minus n dimensional tangent space of the manifold of self-periodic flow states. And the specific matrix element, RMN, corresponds to looking at one specific direction on this tangent manifold. And this means the optical transition between a specific pair of states M and N corresponds to probing the geometry along one specific direction. This establishes the meaning of the optical transition in a geometric sense. And let me remark one thing here. One-dimensional means complex one-dimensional. So to describe this one-dimensional subspace, we need two real momentum coordinate. So it is two-dimensional. Okay, so we've constructed the tangent vector. And then let's define the inner product and parallel transport. Okay, so there is a natural inner product of n by n matrices, which is called the Hilbert-Schmidt inner product. It's defined like this. And this is just the Euclidean inner product of complex matrices as vectors. And what this means is clear in this example. So 2 by 2, for example, 2 by 2 matrices can also be viewed as a 4-dimensional vectors. And the Euclidean inner product of 4-dimensional vectors is identical to the Hilbert-Schmidt inner product of 2 matrices. So yeah, this shows what the Hilbert-Schmidt inner product means. And then the Hermitian metric on this one-dimensional subspace is simply, the inner product is endowed from the inner product of the larger space of all matrices. That is, this is just the Hilbert-Schmidt inner product of 2 tangent basis vectors. And the result is the metric is the product of 2 transition dipole moments. Okay. And then we can also define the parallel transport of 2 tangent vectors. And it is also, this structure is also given by the structure of n by n matrices. If we take the derivative of a tangent vector, we have the parallel components along the one-dimensional direction and their perpendicular directions. But if we take only the parallel part, this is the covariant derivative. That is the parallel transport, and the Hermitian connection is given by just taking the inner product of this basis vector with the covariant derivative. And this can be written like this, and this comma C means the generalized derivative defined by this. So and our construction here, okay, so This generalized derivative is well known in the community of optical responses, but our construction makes its geometric meaning crystal clear as the covariant derivative of tangent vectors. Yeah, so this basically defines all the Riemannian structures of the optical transitions. But in Riemannian geometry, maybe the most important, maybe the most interesting quantity will be Riemannian curvature tensor. So let's define. So we first define the second order connection like this. And by antisymmetrizing the covariant derivative, this simply defines the complex Riemannian curvature, or I will call this Hermitian curvature. And interestingly, this Hermitian curvature is related to the Berry curvature of the M and N states by this relation, which shows that they are intimately related, but they are different quantities. And this Hermitian connection has never been related to physical responses up to date. Yeah, okay. Okay, we have introduced several new quantities, so let's explain what their physical meanings are. The simplest to explain is the Hermitian metric. The Hermitian metric is the product of two transition amplitudes, so this is just simply optical transition rate for constant irradiation. That is, this metric is d and dt roughly. And this can be seen from the Fermi golden rule. Yeah, transition rate is proportional to the metric times intensity. With this interpretation, the Hermitian connection can be understood. Okay, we rewrite the Hermitian connection like this. This is the product of transition rate and the positional shift. And this quantity is actually appeared many times in the morning session. This is the shift vector. That is the positional change between the M and N states. So this Hermitian connection is responsible for the generation of direct current due to the positional shift of electrons during the optical excitation. So this is the shift photovoltaic effect. And okay, this relation between the shift current and the Hermitian connection was previously found by me and my collaborators, but it was only for two-band systems before, but now this relation applies to systems with any number of bands. Okay, and this pattern continues, and the Hermitian curvature is then can be understood as a transition rate of the Berry curvature. And because the Berry curvature is proportional to the Hall conductivity of a band, we can interpret this. Yeah, we can associate with this to the Hall conductivity growing linearly in time for constant irradiation. And if we introduce finite relaxation time, this means that the saturated Hall conductivity in the steady state is inversely proportional to the inverse inverse relaxation rate. Yeah. So this Hermitian curvature is responsible for the so-called injection photovoltaic Hall effect. Okay, let me elaborate more on this effect because this is this relation is quite new. So let's consider the photovoltaic Hall effect. This means that light-induced Hall effect, which is proportional to the intensity of light. And this is described by the third order of conductivity tensor because it involves 3 electric field, 2 from the light and 1 from DC electric field. And these three, third order photovoltaic Hall conductivity in general takes this form. And okay, we say that, okay, it has the Hermitian curvature term. Wow, it's so great, right? Yeah, but this is quite, yeah, very terrifying in this form. But okay, I will show you that this Hermitian curvature term indeed actually dominates at the band edge of topological materials, such as massive Dirac semimetals or topological insulators. So let me take an example. So let's consider one single, Dirac fermion in graphene on the hexagonal boron nitride substrate. This substrate opens the Dirac mass gap, and let's consider illumination of circularly polarized light first. And in this case, our calculation shows that here the photovoltaic Hall effect, shown as the black line, is dominated by this Riemannian curvature term, shown as orange line. So okay, yeah. Oh, okay. And also in 3 dimensions, the similar features appear. Yeah, near the band edge, the Riemannian curvature term dominates. And also for linearly polarized light, we came back to graphene case. Yeah, for linearly polarized light, in this case also the Riemannian curvature term is important in the response, and actually here only the Riemannian curvature term contribute to the response in this simple model. Yeah, and this effect is possible when time reversal and space-time inverted symmetry are broken.
So, oh, okay.
Yeah. Okay. Yeah. Sorry.
5 minutes. Yeah.
Oh, 5 minutes. Okay. Yeah, I was quite quick, maybe. So okay. So in summary, I have introduced a theoretical framework for studying the quantum geometry of optical responses by introducing the idea that the transition dipole moment is a tangent vector, and it showed that the Hermitian curvature is responsible for the photovoltaic Hall effect. And I hope that this made it clear that nonlinear optical responses are promising way of studying the Riemannian geometry of quantum states. And finally, before I end this talk, let me briefly talk about topological aspects. So by applying the Gauss-Bonnet theorem associated with the Riemannian curvature I introduced, we can define topological invariant, the Euler number, which counts the genus of the manifold times the winding number from the Brillouin zone to the manifold. And this manifold is, one can show that in fact corresponds to the Chern number difference between 2 bands. Yeah. So we can define some kind of topology, but so yeah, whether this topological invariant can appear in a quantized optical response is an open question, and I think this is interesting. So I hope you to join this to solve this problem. And this is all. And thank you.
So sorry about that. So first, thanks both Chung and Dimitri for the invitation to tell you about some of the latest work out of my group. And it's also nice to see so many great talks and some old friends. So in any event, I at first felt a little bit out of place here because I'm not really a cat person. I've become a dog person, but hopefully, as you can see, sometimes even us dog people have topologically non-trivial excitations. But Unfortunately, it's not going to be clear how much topology plays a role in what I have to tell you, but it's certainly in the responses that we're looking at. So I'll start by telling you how I got interested in looking at phonons in these topological materials, which is actually for a very different reason, namely that I was really puzzled for many years about why they have these insanely high mobilities. You know, you see these mobilities in these three-dimensional materials that are all, you know, remarkably high, and but at the same time, that's really their transport mobility. Surprisingly, their single particle mobilities, which I'm showing you in green, can be orders of magnitude lower. And so this is a strange case where either they're just only forward scattering, or somehow the single particle is scattering a lot, but yet as a fluid, the electrons themselves are not, and they're giving us high conductance. And I'll give you some sort of hints that we had that maybe the phonons are playing a role. And I'll try to convince you by the end that actually the phonons are primary players in these very high mobilities. So in particular, we've done a series of very high resolution temperature Raman measurements of phonon line widths. We chose Raman mainly because you can investigate both the symmetry of the modes and you don't have any background from the electronic response. In any event, I'm showing you here the line width versus temperature if you want the inverse lifetime or scattering rate. And what you find strangely is in that some of the modes in these materials, instead of seeing them just decrease monotonically because they're decaying into other pairs of phonons in standard anharmonic decay, you actually see the line width sort of plateau and sometimes even come back down as you continue to heat it. And it turns out the reason for that is the blue lines here are fits to Fermi functions. So basically what you're seeing is the phonons decaying into electron hole pairs. And so what that means is the fact that you see this phonon electron decay is unlike a normal system where, say, electrons will scatter and give their momentum and energy into the phonons, and then the phonons will essentially dump it into heat through phonon-phonon scattering. You'll actually see that momentum and energy be, in this case, returned back to the electrons, right? So what I'm showing you here is direct experimental proof that the scattering rate of the phonons into the electrons is much faster than the rate of phonons into themselves. So there's a long-winded way of saying that it must be the case that in these materials that the electrons and phonons, especially in non-equilibrium, move together as a fluid because basically they're constantly scattering back and forth. And so the reason for this high transport, and we believe, is due to the fact that although momentum can be lost by an individual particle, by the collective, if you will, they move together. So then I'll try to tell you a little bit about what we think are the origins of this in these various materials. And essentially, there are two key ingredients. So I'm showing you here a first principles calculation from our collaborator Prina Rung at Harvard, where she finds that the acoustic modes do what's called bunching, which is to say that the longitudinal and transverse modes are very strongly overlapped, and this dramatically reduces the phase space for phonon-phonon scattering. At the same time, you have band structures which sort of allow for a lot of nesting. So in other words, there's many options for various phonons to scatter into electronic states. And we believe that it's this combination of a large phase space for phonon electron scattering and a reduced phase space for phonon-phonon scattering that allows this all to happen. And if I have time, I may say a few words about how I think, although I should admit we're hearing a lot of this from others, but how I think this could be extremely interesting in terms of both topology and transport properties and nonlinearity in these materials. Okay, so if I have time at the end, I'll also tell you about some new recent results from my group. Actually, these results were discovered later, but published first, as sometimes goes, where we found that ruthenium chloride is a 2D material that has a very deep work function. So as a result, if you put graphene or other 2D materials onto it, it soaks electrons and acts like a modulation dopant, like in semiconductors. The cool thing here is that means you must have a very strong built-in electric field breaking inversion. And so we're quite interested in this in terms of, again, its ability to turn on nonlinear responses or enhance them. Okay, so just to go back, I want to, again, say that when, graphene and other Dirac semimetals came about, at first people were not surprised by the fact that they had high conductances or high mobilities, because of course in a normal metal you have lots of phase space for scattering, but of course in a Dirac system you dramatically reduce the phase space for scattering, whether it's electron-electron or electron-phonon. And so initially it was thought that indeed you should have a high phase space. Of course, in addition, these nodes are protected by symmetry, and so you might imagine that symmetry is playing a role in reducing the scattering. And so that sort of suggests that these Dirac systems, could be good for very high mobilities. The strangeness, I would say, is that you see this in a wide range of materials. So for example, in cadmium arsenide, which we heard about earlier, is a bulk Dirac system with a very high mobility, and yet the single particle scattering rate is orders of magnitude higher than the transport scattering rate. You see that in tantalum arsenide, which is a 3D Dirac system, and of course has actually effectively a large density of states because you have many nodes and you have trivial bands. You see it in WT2, although it has a lower mobility, it's still very high. And again, this is a type 2 Weil semimetal. And perhaps most dramatically, you see this in WP2, which although it's a type 2 Weil semimetal, it actually, as I'll show you later, has nodes that are something like 250 MeV below the Fermi level. So their relevance to transport seems very unlikely, right? So now you might have also argued that actually Dirac knew this all was coming, and in fact, you can see he was quite interested in tilted cones, but it's really hard to see how, how one can just explain away all of this as reduced phase space or symmetry when you have these materials, all semi-metals, but nonetheless with very different Fermi surfaces, giving you this remarkable transport. So just to show you how remarkable it is, and this was also what really surprised me maybe 4 or 5 years ago now, was there was this nice work out of Florida where they showed they could grow tantalum phosphide, and also the same was true for tantalum arsenide, and you would have enormous numbers of defects, lots of anti-sites and stacking faults and so on. And nonetheless, they could see quantum oscillations with mobilities on the order of 10 to the 4, 10 to the 5. Right, and this was originally attributed to maybe chirality protection or topology, but I think it's clear that that can't be the whole story. So WP2 came along, and a number of us were quite excited because this is a material where the nodal rings, which give you the Weil semimetal, the Weil points, the rings of opposite Chern number are actually well separated in momentum space. So once you gap them out with spin orbit coupling, there was no chance that the nodes would annihilate, and more importantly, they'd be far separated in Q. Unfortunately, the Weil node, as I said earlier, is buried deep. It's about 250 MeV, and so you actually in this material have fairly large Fermi surfaces, although it's a fairly compensated system. WP2 also has other remarkable properties. So if you look at low temperatures, the transport shows its mean free path is on the order of 100 microns. And there's been a number of claims of hydrodynamic transport, electron transport in the system, and observations of an extremely strong violation of the Wiedemann-Franz law. And like many other of these semi-metals, what you see is that the triple R ratios are just enormous. You see changes of many orders of magnitude in the resistance versus temperature. And in fact, the resistance is often claimed to be thermally activated, which is strange because it's not a semiconductor. But in fact is attributed to Umklapp scattering. So basically at low temperatures, you have no Umklapp scattering, and that strongly turns on, and that's essentially killing the effects that I'll tell you about later. This Umklapp scattering is, again, suggestive of the fact that you have phonons playing a key role. So the other interesting aspect is, of course, if you think about, if it is chirality or symmetry that's protecting you in a given node, you would expect that it's phonons that in principle could take you from one node to the other, although you might start to worry about angular momentum. But in any event, and so that suggests that the phonons could play an important role in, say, killing some of the effects that we're all interested in, like the chiral anomaly. Okay, so just as a little bit of background, for those of you who are not so used to thinking about phonons in their lifetime, so the typical thing that happens in most materials, especially if you're measuring an optical mode, is that you'll have basically phonon-phonon scattering where your optical mode will decay into a pair of acoustics, right? And as long as you conserve momentum and energy, you basically can have this process. And so what you normally see is the lifetime grows with temperature just due to the Bose factor probability of creating your modes. However, there was very nice work done in Los Alamos, actually, about 3 years ago in tantalum arsenide, where they showed that actually the infrared mode that they saw, its lifetime actually was reduced with increasing temperature, which was quite anomalous. And this was attributed to the fact that this mode could decay into electron hole pairs across the Dirac point, and therefore its temperature dependence is just governed by a Fermi function. So if that's true, again, it means that the phonons are scattering more off of electrons than they are off of each other. And as I'll show you later, that enables you to enter a new regime, which is called the phonon drag regime. Okay, so we went and looked with Raman. We wanted to get rid of, as I said, any metallic background or any other contributions and be able to understand what happens in different symmetries. So what we found in tantalum arsenide and the same in niobium arsenide is that basically the phonon line width just grows with temperature like normal anharmonic decay. However, there are other modes of different symmetry, so in this case A1, where they actually do, they grow and then they peak and then they start to come back down. And this really confuses us at first until we saw this paper of the infrared work and realized that it must be a similar explanation, namely that your phonon is decaying into electron hole pairs. And what's remarkable is that in modes that show this behavior, you always see much shorter lifetimes or much wider line widths, suggesting that, again, the phonon electron scattering is a much stronger effect. Now, the thing that worried us, though, is that, of course, what it suggests is that your phonon comes in and it sends the electron from below the node to above it. The problem with that is that it would require the phonon to flip the spin, which is obviously not possible, especially for an A1 mode. However, working with Pri Narang's group, we realized that there's a reciprocal lattice vector that will take you essentially from one node to the other, again, with a combination of this optical phonon, and that the phase space for that process is enormous. And so there's actually a large way, if you allow for sort of Umklapp-like processes, where you can scatter from one node into another. Now, at the time, we didn't quite realize the importance to transport, but we still suggested that this meant that there could be interesting, strong electron-phonon coupling in these systems. So we decided to then look at WP2, which, as I said earlier, has this buried node, to see if you see the same effect. And sure enough, you do. You actually see that there are two A1 modes there that have very strong phonon electron scattering. And sorry, I forgot to mention in the tantalum arsenide, those two modes I showed you earlier are basically of the same energy, maybe very slightly different, but just of different symmetry. And so it was suggestive it was the symmetry which was controlling the effect. In any event, sorry, so in WP2, we see this very strong effect again. And what we realize is if you zoom in on the Fermi surface, in this case, you don't have a Dirac-like system. You have these linear bands, but these linear bands allow you to have many, many places where this electron can be excited by a phonon into the other band, right? And it turns out both for intra and interband transitions, this is very likely. And there's a huge phase space available for this decay of the phonons into electron hole pairs. And so this directly showed experimentally that, again, that the decay of the phonons into electrons was stronger than decay of phonons into each other. And just to show that more convincingly, here is a third mode, which again was close in energy to these other two, where it showed almost no temperature dependence from the anharmonic decay and had a much lower scattering rate. Okay, so what's the implication of all this? So let's ask, why do we normally think that phonons are bad for transport, right? And the reason is, you imagine with an electric field exciting your electron, the electron scatters off an acoustic mode. As a result, it loses momentum, and the momentum and energy goes into the acoustic phonon. And that acoustic phonon then decays by anharmonic decay into other pairs of phonons, and so on and so on, right? So what that means is I'm trying to give momentum into my electron fluid to get a current, and that current is being reduced by the fact that electron-phonon scattering is sending the momentum into the phonons, and by phonon-phonon scattering, they are basically losing all that momentum and energy to heat, right? Essentially, it's why you get heating. Okay, but the key assumption here is that acoustic mode primarily decays off of other acoustic modes and does not scatter into another electron, right? If it did, if that phonon electron scattering was dominant, then it means that the momentum that the phonons had grabbed would be returned back to the electron fluid, right? Now, of course, for a single particle, there could be lots of scattering, but for overall the Fermi surface, you would still get a large enhancement in the momentum, right? So basically, you can think of it like the phonons and electrons would essentially be moving together. the phonons would be dragged by the electrons along. Okay, and the result of which is you should get a strong enhancement in the conductance. And this is, in fact, what we are directly seeing, right? Because in WP2, we're seeing that the phonon decay rate is bigger than the phonon-phonon. When we worked again with Pri Narang, what we realized from her calculations is that this is in fact due to the fact that your acoustic modes, first of all, their bandwidth is actually quite small, but secondly, the splitting between the TA and LA is small, as I'll show you in a minute. But more importantly, through her first principles calculations, she can actually calculate the phonon-phonon and phonon-electron scattering. And what she finds is that at low temperatures, the phonon-electron scattering, even for the acoustic modes, is 10 times what it is phonon-phonon. So in other words, that you really do have this dominant phonon-electron scattering in the system. And this is really, I think, the first, or maybe the first direct proof of this idea due to Peierls from 1930. And we believe is really key to this large mobilities that you see in many of these systems. So what is it about these systems? What are the ingredients that really lead to this effect? Okay, so the first question you might have asked is what happened to the inharmonicity, right? So again, remember, normally you imagine a phonon decaying into a pair of acoustic modes. However, of course, normally your TA and LA modes are split. And so there's actually a large number of possibilities where you can have a mode decay, right, and still satisfy energy and momentum, right? And so that large, the splitting leads to a large sort of effective state, number of states or phase space for scattering. But as I showed you earlier for WP2, and it turns out Pri's calculations show this also for niobium and tantalum arsenide, the TA-LA splitting is actually quite small, right? And so this phase space for decay into acoustic modes is quite limited. And it turns out that this is not an idea that we had. It's actually an idea due to my colleague, David Broido and others, that actually is called acoustic bunching. Okay, and David actually used this to explain how you can get very high thermal conductivities in a variety of other materials. So again, here's WP2, here's niobium arsenide, and again, you see this overall, reduced bandwidth of the acoustic modes and this bunching of the transverse and longitudinal acoustic phonons, which would reduce your phonon-phonon scattering phase space. Okay, so what is it about these materials? So the honest answer is we don't know. But we have some ideas. So let me give you what we've noticed, which is, I should say that there's also Raman data in MOT2 and cadmium arsenide that shows the same effect, although it was not properly identified at the time. In any event, so in all these materials, we noticed you have one heavy atom, which of course will reduce the overall bandwidth of your acoustic modes in general. You also have one light atom, and it turns out, of course, whenever you have a heavy atom and a light atom, you'll get large optical acoustic splitting, and so that could, in principle, reduce further your bandwidth. Why it reduces the splitting between transverse and longitudinal modes, we honestly don't know. So if someone does, please tell me. In any event, the heavy atom is, of course, what gives you the strong spin-orbit coupling, which we love to give you the kind of Fermi surfaces we're interested in for interesting quantum geometry. But nonetheless, we believe that's what's giving you this large phase space, or essentially Fermi nesting, Fermi surface nesting, which allows for the phonon electron to dominate, right? So it's basically this combination of the acoustic bunching and the nesting of the Fermi surface, allowing for phonon electron decay. So I just want to briefly talk about some of the consequences, right? So if you really have this strong coupling between the electrons and phonons, and you have what's called a phonon electron fluid, there's actually predictions that this in and of itself could give you hydrodynamic behavior. That this can be a way that you have strong momentum conserving scattering, and it's the joint fluid of the electrons and phonons which could give you this hydrodynamic behavior. And in fact, there's very nice work out of Harvard from Amir Yacobi's group in collaboration with Pri Narang again, where they looked at how the current is distributed in a WTE2 Hall bar, and they look at its temperature dependence, and they find that they can only really describe that properly if they account both for the standard electron-electron and the phonon-electron scattering. I'm also quite interested, and there's some predictions here that, could you get strong nonlinear responses this way? So in the same way that people often talk about hydro giving you nonlinear responses, but how, just from the fact that you have this strange coupled fluid of the phonons and electrons, how might that lead to new and interesting nonlinear responses? For example, if I send acoustic modes into my system, Can I observe that in the optical responses? Similarly, can we use this for topological control? So, there's some who have talked about strain fields, but here this suggests that the dynamic strain of the phonons will of course couple strongly to the electrons, and how can we use that for topological control? And last but not least, I think one can ask, can we do similar things with magnons? Are there magnetic systems where we could essentially use the magnons for the same purpose? And I'm just throwing that out as an idea for discussion. I really have no idea whether it would work or even what the right system would be, but if someone does, I'd love to chat with you about it. And that's certainly, by the way, something we can measure in Raman. We can look at magnons and magnon lifetimes and so on. Okay, so in my remaining few minutes, I just want to talk a little bit about the future, which looks very bright these days. So I'll tell you about some of the things that we have in my going on in my lab. So we have what we call a clean room and a glove box, which we've developed over many years with lots of capabilities. Like many others, we can do 2D transfer. We can also write with a massless lithography system. We have in situ Raman and AFM. So if you have air sensitive materials you need help with characterizing, we can do it. And also we have E-beam and thermal deposition. So we can also make full devices inside this inert atmosphere. About 6 months or a year ago, we added this vacuum suitcase to the back, which is quite an exciting new capability. So it means that we can take materials that we make in the glove box, or we say freshly cleave in the glove box, and we can bring them to our low T optics and transport setup. So we can actually, we've now shown a number of air sensitive materials where Raman signals were dominated by oxygen responses we can get rid of by just cleaving them in our glove box and transferring them over. We also, inside this system, can do photocurrent and other transport measurements. One aspect which we haven't explored yet, but we're quite excited about, is in principle, we could then also use this to take films from MBE and then combine them with exfoliation, or inversely exfoliate and then bring our exfoliated pieces to MBE. And similarly, can we combine this with, say, STM or other near field type probes, which is something we're very interested in doing. And I should say this is not all in theory. There's actually a number of publications that have come out of this system, including our recent review of scientific instruments, if you want to see more of the details. So last but not least, I mentioned we recently made a new discovery in ruthenium chloride. Namely, it has a very deep work function. We didn't discover that. That was known for a while. And it's a relativistic monoinsulator. So it has well, not a flat band compared to graphene, but or twisted graphene. It has about a 0.25 eV bandwidth. So anyway, the point is, if you put graphene onto ruthenium chloride, because of the difference in work function, you get an enormous amount of charge transfer, more than you can get with a gate. You can do more with ionic liquid, but of course not as cleanly. It turns out this works for bilayer graphene, and we have some evidence that this probably breaks inversion in the bilayer because it mostly soaks the electrons from the bottom layer. What's more, if you put HBN in the way, it turns out HBN's valence band is roughly resonant with the conduction band of ruthenium chloride, and so you can still get charge transfer through the HBN. So you can imagine using this in very high quality materials or devices to then induce charge transfer via what's often called modulation doping, which was originally invented at MBE to get to the high mobilities needed for fractional quantum Hall. What's also fantastic is it's not limited to graphene. So tungsten selenide has roughly the same work function, and we find that this works to p-dope tungsten selenide. And just to show you how short range this is, I'm showing you Raman data now, and I don't have time to go into the details, where we're basically optically measuring this charge transfer. And this is a piece of graphene which is covering partially SiO2 and partially ruthenium chloride. And you can literally see the border of the ruthenium chloride doping, showing that it's a very short-ranged effect. And what's more, what I'm not telling you is this is single layer ruthenium chloride. So even just a single layer of ruthenium chloride is enough to generate this charge transfer and strong built-in electric field. And there's also work out of the Bassoff group showing that this can be used for very high quality plasmonics. So we're quite interested in thinking about, can we use this to break inversion and maybe do plasmonics to really enhance or create new nonlinear effects? And we're more than happy to collaborate with others on this. By the way, I should say also there's interesting things to be done in tungsten selenide. All right, so I think I'm about out of time. So let me just thank the various people who made this happen, in particular Gavin Osterhout, a recent graduate of our group, and Vincent Blisson, a current graduate student who did all the measurements I showed you. Lots of theory help, especially from Prina Rung's group and discussions with Ing Ron, my colleague. Great samples from Nini and Claudia Felser's group. And most importantly, of course, thanks to the DOE for their continued support of this work, hopefully continuing on after this year. In any event, the glove box I showed you was built by a fantastic grad student, Mason Gray, who's now looking for a postdoc, if anyone's interested, and with support from various places. And the ruthenium chloride work was done primarily by Yiping Wang and very close collaboration with Eric Henriksen's group, with usual sources for samples and lots of theory help from Una Kim and Li Yang. So just to summarize, I hope I've convinced you that the transport in these topological semimetals is in and of itself a non-trivial, just for the extreme high mobilities, that we've directly observed that the phonons primarily decay into electrons, suggesting that you have these coupled fluid, and that the reason for that is this combination of acoustic mode bunching and Fermi surface nesting. And so with that, let me thank you for your time. Gladly take any questions.
All right. Yeah, thanks so much. First, I'd like to thank the organizers for giving me this great opportunity. It's great that I can present a bit of my recent works, even in this tough times. So thanks so much. So today I'd like to talk about photocurrent from X-stone and polariton excitations, which is composite particles rather than just a free electron holes. So this is the big idea of this today's talk. So the first one is a geometry and topology, which is becoming more and more relevant in recent studies of condensed matter research. And the other topic is the main theme of this workshop, which is nonlinear responses. And for example, nonlinear responses include many interesting phenomena such as photovoltaic effect or high harmonic generation. Also, the nonlinear transport is very interesting and useful nonlinear functionality. And in this talk, I like to present a few examples where notion of geometry and topology is very important in the field of nonlinear response, especially focusing on the coupling through Berry phase and Berry connection. So this is the plan of my talk. First, I like to introduce a shift current, which is a typical geometric nonlinear response characterized by Berry connection. And then I like to talk about recent my works on shift current in multiferric materials where magnons can exhibit shift current response. And then I like to talk about photocurrent from X-stones and polaritons, where the steady DC current flows, which is proportional to polariton density. So first, let me briefly talk about the general second order nonlinear optical effect, where the current is proportional to two incoming electric field. The typical example is shine the laser light to the material, and then we have some frequency generation and a different frequency generation. And in today's talk, I like to focus on this difference frequency generation or the terahertz emission. And this is typically the mechanism for solar cells, because it's just a shine the light to some material, and then we get the current. So this is basically the solar cell action. And in the field of the solar cell action, one of the interest is the new kind of solar cell materials made of perovskite, which shows a very efficient solar cell action, which is comparable to the conventional silicon oxide, silicon cells. And this is the typical examples of perovskite oxide, which shows the photovoltaic effect in bulk materials. This is the typical ferroelectric material showing the polarization hysteresis like this. And in its polar phase, once we shine the light to the sample, it produces the photocurrent. And if the sample is pulled in the opposite direction, we can reverse the direction of photocurrent, and it turns out to be very efficient. And many people are interested in this kind of new type of perovskite solar cell action. And the one interest is what is the mechanism of such photovoltaic effect. In conventional solar cells, like PN is made of PN junction, where the silicons in a p-doped and an n-doped are made like this heterojunction, where we have a band bending like this. So if we shine the light here, we can create the electron holes, which is dissociated with this band bending, and we can generate the current response. On the other hand, in such a perovskite solar cells, it's made of a bulk crystal, and we don't have any this type of artificial structure and a band bending. But on the other hand, we have a non-central symmetric crystal structure like this, and we have a polarization where the polarization induces kind of a built-in electric field, and can be thought as a main player that dissociate these electron holes in these bulk crystals. And now one candidate mechanism for such a efficient photovoltaic effect is shift current, which is a DC current proportional to E squared, and can be usually present in non-central symmetric crystals in general. And one example is this kind of barium titanate, where the first principle calculation predicts this kind of frequency dependency, and it kind of coincide with the experimental result like this. So this is a very famous example of a shift current in ferric materials, and then there is also other calculations for example, ferrite materials are known like this. And usually the shift current is its calculation is based on the perturbation theory, which is usually very complicated because it needs information of the old bands. So we wanted to construct a more concise theory formalism for shift current. So we developed another way, another approach, which is based on Floquet theory formalism. And then we applied it to the nonlinear optical response. So Floquet theory, to be quick, it is a kind of time direction analog of Bloch theorem. And we have a second Brillouin zone and a third Brillouin zone in the energy direction. So in short, we have a copy of bands in energy separated by photon energy. And if we combine this technique with Kalish-Green's function, which generally treats the non-equilibrium phenomena, we can construct a general formalism to describe nonlinear optical response. There, bands with for example, we have a situation like a conduction band and one photon direct valence band is crossing with each other. So Floquet theory is a band theory. We can have a band anti-crossing like this, and such anti-crossing of Floquet bands describe the non-equilibrium steady states in Floquet theory. And if we look at the Berry phase or Berry connection at these anti-crossing, we actually find the concise formula for shift current like this. So this is the formula, and the photocurrent is proportional to the delta function, which specifies where the optical transition takes place. And this V square is basically the dipole matrix element squared, which determines the transition rates. And this factor with gamma is the saturation effect, where the gamma is the scattering strength. And finally, this object here is called shift vector. Phi is the phase of velocity matrix element, and A's are the so-called Berry connection, which is geometric object. And since the Berry connection contains the k derivative, due to the canonical relationship between position and momentum, k derivative is basically the measure the position operator, position of the wave packet. So this A1 minus A2, which is the Berry connection difference between the valence and the conduction band, and this measures the how the wave packets are shifted in the unit cell before and after the optical transition. So shift vector is the geometric object which bridges two manifolds, which one is the valence band and the conduction band, and then it measures the difference of the local geometry, which is intuitively just a shift of the wave packet in real space. So more cartoonish picture is like this. So suppose this is a ground state, and we have valence electrons sitting at some orbital, and once we shine the light and then it create the electron hole pairs, the electron usually, in general can hop into the transition into the another orbital in the conduction band, and then the position of its wave packet can be different in inversion broken materials. So light radiation basically shifts the wave packet by optical transition, and as such shift moves the electrons, and then in the steady state, this gives rise to electron flow. So the picture of the shift current is basically that the electron hole pairs have a finite polarization P, and if we constantly create the such electron hole pairs, the polarization increase in time, which means that since the time derivative of polarization is current, it means the DC current generation. Let's see. And such shift current is measured in several materials, including the semimetals. But let me show here the ultra fast spectroscopy of shift current in antimon sulfur iodide, which is a typical ferroelectric material. So the people in Ogawa's group in Riken at Tokyo measure the terahertz emission from the sample with a laser excitation, and measure basically the current density as a function of time above the band gap and below the band gap. The below the band gap, it has only the polarization induced, and it disappears after light pulse. But above the band gap, it shows the shift current, net current generation, and it is observed in a terahertz experiment. And also the power dependence shows this kind of saturation effect, and it coincides with the Floquet theory prediction. This is a fit. It is from this Floquet theory, and then it shows the nice coincidence. It also points to the shift current mechanism for this photocurrent generation. Next, I'd like to talk about shift current in multiferric materials. So the motivation here is how does the electron correlation modify or enhance the shift current response? And because so far the shift current is discussed on basically mainly for the free electron hole pairs, but the photo excitation of collective modes in correlated materials can also induce the photocurrent, and hopefully it can be giant because the collective mode gather the many oscillator strength from the higher energy bands. So one typical example is such magnets like this. So shine the light to the magnet and then induce some spin wave, and we want to ask if it can generate some currents. So the setup is this kind of multiferroic materials where the polarization and magnetization is coupled. Since this coupling, multiferric coupling, the electric field can induce the magnetic excitation, which is known as the electromagnon, and measured as a dichroism like this. So our question was whether we can observe a photocurrent by exciting such kind of electromagnons in multiferric materials. So in order to demonstrate this idea, we constructed a 1D toy model of multiferrics. Basically, this is just a ferromagnet with a Hubbard interaction and a spin anisotropy. And then we also included the spin orbit coupling, because the excitation of electromagnon required the spin orbit coupling. And in order to induce the inversion braking, we included this type of a staggered potential that breaks the inversion symmetry. And then we, in this toy model, in the ground state, we have ferromagnetic states in the mode phase, and we can excite magnon like this. So we hop the flip the spin from up to down by spin orbit coupling like this, and if we further hop this electron from here to there, then we get the electron hole pair at this site, which is actually triplet exton, and then this is nothing but the magnetic excitation or magnon. And we computed this excitation by a diagrammatic method, and then obtained the magnon dispersion. And also we use the diagrammatic method to calculate the second order nonlinear conductivity, and then we got this spectrum where we have a nice peak structure at the magnon excitation. So in a flat band limit, the conductivity is proportional to the magnon excitation. So this clarifies that even magnon excitation, which is really low excitation compared to the band gap, it can also generate the photocurrent response. So the mechanism here is again shift current mechanism. So magnon creation in multiferric materials, magnons have polarization. So they are electromagnons. So polarization increases as with time in a constant light radiation. So the constant increase of polarization gives rise to shift current. So this is the mechanism for magnon shift current. So let me explain other similar mechanism for shift current with bound states of electron holes, which is the excitons. So as you know, so excitons are made of attractive interaction between electron holes, and this is the band gap, and then the magnons. Oh, sorry, these excitons are formed below the band gap. So they are charge neutral. So there's no free electron and a hole pair. But still, if we calculate the shift current by, for example, by Floquet formalism, we can get that photocurrent response by exciting excitons. This is the full formula, but the important part is here is the delta function corresponding to the exciton excitation, and R is again the shift vector. And then here the shift vector basically measures how electron hole are separated in each exciton, or each exciton, how much polarization each exciton has. So surprisingly, this formula shows that the charge neutral excitons can also induce the DC current. So this is basically driven by the non-zero polarization of extons characterized by shift vector or Berry connection. Actually, this exton shift current is observed in typical exton semiconductor cadmium sulfur, where this is the terahertz. Again, this is a terahertz experiment. The A exton is sitting around the 2.5 electron volt, and this is the band gap. And then this is the spectrum of the photoconductivity, or sigma 2. And in addition to this bulk above band gap spectral weight, we can see the shift current peak at the A exton below the band gap. Also, the time profile of this A exton peak. This is around the 2552 here. This also points to the shift current time profile compared to the below gap, just a usual optical rectification signal. So now the extons are now it is known that the extons can produce a shift current, and similar bound states is known, which is exton polaritons. The polaritons this is actually the main part of my talk, but the polaritons are combined coherently mixed state of extons and laser light or external light. So typically, this can be realized in the cavity with quantum dots, quantum wells. In the quantum wells, extons are formed like this, and if it's put in the cavity, it couples with the photons. So this is the band structure. So this is the band structure of exton, and this is the band structure of cavity photons, and then they can couple with each other and hybridize. They anti-cross with each other, and this lower band is called a lower polariton, and then this is upper polariton. And then if we make these band structures very suitably, we can gather all the polariton density into the bottom of the lower branch like this, and since the polaritons are bosons, it can condense into the polariton condensate. This is the Stanford experiment. So the question here is that do polaritons support photocurrent like extons? And to solve this problem, we started with this phenomenological Hamiltonian that couples the extons and photons with this light matter interaction, and then we get this polariton bands, and the photocurrent arises from the diamagnetic coupling between exton and photons, and looks like this. So the current is proportional to A dagger B, so photons and the extons, and then this is basically the bilinear form of polariton operators. And if we do some math, we can show that the photocurrent is proportional to polariton density in the lower branch minus upper branch like this. So the photocurrent is proportional to polariton density itself in this case. So we can do the microscopic derivation. We can skip this part, and we did calculation or proposal for transition metal dichalcogenide. For example, taking that two-band model like this, and we need to. It turns out that we need to break the time reversal symmetry because it's like a Hall current actually. So we need to apply the strong magnetic field to induce Valley asymmetry, or we can use the cavity photons or circular polarization. In any case, we can get a few millielectron volt to the 10 millielectron volt coupling. And then as an order estimate goes like this, and then and with some math, we can get the photocurrent of 30 nanoampere for a typical polariton condensate case, which is experimentally feasible. So to summarize, I talked about shift current, which is a geometric nonlinear response, and introduced the electromagnetic shift current, and also the I explained the photocurrent from exciton and polariton excitations, which is the bound states. So this is the last slide. The outlook is a geometric nonlinear effect is a very promising field, especially the strongly correlated materials are less investigated. For example, superconductor, multi-insulator, heterostructures. So I think in this field there are more to come. Thanks so much.
Yeah, hello, I'm Bing Hai from Weizmann Institute. First, thank the organizers to organize this nice event. My talk here will be about this nonlinear response in twist bilayer graphene, and a slightly different material here. Okay, let's go. Let's see about nonlinear response. Already a lot of explanation of the mechanism here. I just use this very naive picture, like when we shine a light to a material, sometimes we can get a second order response. This is a textbook effect for the second harmonic generation. We have a polarization. The change of the polarization actually is the current. And here, easily we can understand, because of the E square, the current can be a DC current. A minimal requirement for this phenomena to get this DC current is the inversion. The system should be inversion symmetry breaking. And then this phenomena looks like a solar cell. We shine a light, then we get a DC current output, like this PN junction. But this can be realized in a homogeneous solid material. Then we see this wire semimetal barrier curvature a lot. Also, another nonlinear phenomenon is the nonlinear anomalous Hall effect. And then here, this wire semimetal, it represents a kind of highly dispersive band structure with a tiny Fermi surface, and there are multiple of this barrier curvature. And this is the kind of big motivation to trigger people's interest in this nonlinear phenomenon. Oh, sorry, what happened? And today I will talk about the similar phenomena in twist bilayer graphene, and is represented in band structure almost a kind of opposite limit. It has super flat band, and the Fermi velocity is quenched. And about the similarity is, usually it's not much recognized actually. A twist bilayer graphene, twist by definition is chiral. This is a chiral system. It's breaking inversion symmetry. And for symmetry consideration, nonlinearity should come out. And then next, I will demonstrate you that actually the flat band will be kind of advantage and to enhance this nonlinear effect. Okay, we go. First, I will talk about this shift current in twist bilayer graphene, and then I will go to another phenomena, the special magnetic resistance. This is the longitudinal resistance. If I have enough time, I will flash about this nonlinear anomalous Hall effect. And about shift current, and this is generally like E is the electric field from the light, and this is the DC current mirrored. This is the photoconductivity, and this formula we see a lot. This is this important quantity. This is the shift vector. This is considered just a phase, and add this phase to keep this quantity gauge invariant. Because R is related with this barrier connection, and kind of plausibly we believe this is a huge barrier curvature can enhance this shift vector. And recently we developed something slightly different understanding, and for the shift current. Actually, we try to develop a picture called anomalous acceleration. we know in linear response about anomalous Hall effect, very important concept is the anomalous velocity. When we talk about nonlinear response, and here we introduce the acceleration. We can simply understand for wire semimetal this. Actually, wire semimetal, we know this is almost massless, has super high velocity. And then therefore in real space, its wave function is highly delocalized. And for this massless particle, it's very easy to accelerate it, right? This huge acceleration is a kind of source to enhance this nonlinear fluid current. But follow this logic, we go to the flat band. Actually, flat band, we know flat band system in real space is very localized, and it's the opposite. And its mass is huge. It's very hard to accelerate it in real space. However, there's a duality in momentum space. Because this motion for quantum particle, we cannot completely separate the real space and momentum space. Actually, in momentum space, it's distributed in a big phase space. And this anomalous acceleration picture also works in momentum space. Therefore, for flat band system, the momentum space acceleration maybe is a way to enhance the photon current. And you may ask, what is the in-between? Actually, in-between is just the ordinary material. We have a huge Fermi surface, and it's also kind of relatively dispersive in real space. And here, this wire semimetal and flat band represent two limits. Go back to this old formula. Actually, for us, we rewrite these two parts. Before, this phase term is considered just a correction. And actually, just a correction, put a phase there. And here we pointed out, actually, this term corresponding to exactly the momentum shift. And the real space shift is same, is exactly this part. And the momentum is separate. And you see the Barry curvature here. This is the change of the Barry curvature. Actually, this is the Barry dipole that induced the nonlinear anomalous Hall in the DC limit. And this part is related with another quantity called quantum metric. Actually, quantum metric and Barry curvature together, they are the quantum geometry. This is just quantum metric is the real part. Okay, this is the details, but the important is here, we can make a separation. But overall, anyway, they are the same formula. Whatever you do, we use this, either this formula or this formula. We calculate, let's see the numerical result first. And we start with twist bilayer graphene band structure. And this band structure, we use this continual KP model. But although twist bilayer graphene is chiral, unfortunately, this KP model, like this effective model, it has inversion symmetry. Then for this reason, we have to break the inversion, and this usually happens from the substrate. And with the inversion breaking, this is the new band structure, and it's slightly different from what you see in the literature because we break the inversion symmetry here. And then we calculate the nonlinear conductivity. And this is the light frequency. This is the photocurrent response. Well, first, this value is kind of big compared to ordinary 2D material. But here we put the frame energy. We changed the frame energy chemical potential into this 3 gap. This is single particle gap. And we all see very large response. And interesting also, like we see the omega coordinate. This is generally in this terahertz region. And we have an argument kind of because, yeah, this peak corresponding to exactly these band gaps, these resonant band gaps. We have argument like this shift current maybe is a good, in twist bilayer graphene, maybe is a good candidate to detect this terahertz radiation. For terahertz radiation, like we know this is a challenging job and ordinary semiconductor cannot work out. And this is the infrared detector. This is a mercury cadmium telluride. We know this band structure, mercury telluride, very well from the topological insulator. And we mix these two material, because this is a negative gap, this is a positive gap, we can fine tuning the band gap. However, when we go to the terahertz region, the finite band gap, like it's competing with the temperature. always competing. Actually, it's much smaller than room temperature. And go to the terahertz region, the thermal carrier can easily kill the signal, because this semiconductor device just depends on the photon excited carrier. There's another design, like actually these days people try to different way, like use plasmas in graphene and for terahertz detection. And here, like we pointed out, like actually this shift current, like first, we know shift current is not sensitive to scattering, to temperature. It's for a simple reason, just like anomalous Hall effect, because it's an intrinsic property from the geometry or from the band structure. And therefore, we don't have to worry too much about the scattering, the impurity for shift current. And good thing is for twist bilayer graphene is the band gap is at the right region. Then this is the ideal choice for terahertz. Okay, go back to the argument. I promised, see, there are, for twist bilayer graphene, we should have a huge momentum shift and smaller real space shift. And this is the anomalous acceleration picture. And then what's the numerical result? Let's see, we separate the total shift current. And this is the momentum one. And this is the real space one. For TBG, indeed, the momentum one is dominant. And we compare with another material, MLS2. This TMD material, actually, MLS2 is the real space, the ordinary material, real space dominant. Okay, we move forward to like in the shift current picture, like we shine a light, we kind of use a single phase material like a PN junction. And we shine a light, we get current. Then PN junction has another well-known property is to rectify the current. And the current is this longitudinal current. And then we may ask, can we mimic this PN junction more in a single phase material? Like this shift current, we already get it. And can we do more? Actually, there is already this phenomena is reported called unidirectional magnetoresistance. About the resistance of a material, we know we really don't care about the direction, right? The left and the right current usually give us the same resistance. About years ago, this is found. Actually, for some material, the resistance, if you have a magnetic field, then it depends, there's an I dot B term. And this prefactor actually is determined by the chirality. The first experiment was done, let's use a bismuth metal, twist this metal, make a helix. And this helix, like as long as it's helical, it will give you a current-dependent resistance. You see clearly, when we flip the direction of current, all the direction of magnetic field, the resistance will change. And therefore, your IV curve, your voltage will depend not only the linear part of the current, also the quadratic part. Actually, this does not violate any reciprocal relation. The unsagred reciprocity requires when we flip magnetic field and current, the resistivity does not change. This does not guarantee if you only flip one, and they will remain the same. And actually, this phenomena in recent years has been studied in many other materials, especially inversion breaking material. For example, this is the bismuth telluride bromide. And the physical origin, yeah, by the way, the experiment usually done is you pass a current, the current usually is AC, then you measure the voltage. The voltage, actually, you can find a second harmonic signal from this I square dependence of the voltage. The physical origin is extensively studied by Nagosa, Morimoto, and their colleagues. And it's closely related with the asymmetric spin scattering, dissipation, the chirality, and the way of the inversion breaking. I try to think, like make this picture even smaller, like simpler. Like we always like some intrinsic property, like anomalous Hall effect. We like the intrinsic barrier curvature, and the shift current. We talk about this this shift, this barrier connection, anomalous acceleration. And can we simply think something from the band structure to understand this unidirectional MR? Yeah, now let's start from a simple 1D band structure. The precondition is the material should break invariant symmetry. But whatever, we will have a band structure like this. The K minus K, they are symmetric because time also symmetry. But when we apply magnetic field, we know magnetic field like will break the symmetry, like make K minus K different. This is the consequence of time also breaking. Therefore, these two velocity will be different. This is all we observe. But if we ask about the conductivity or resistivity of such 1D system, usually in the ballistic limit, the conductivity is only related with the channel number. It does not care about the velocity. In the diffusion picture, if we have a huge sample and the conductivity is related with the density state, the Fermi velocity square, and the relaxation time. And we don't care about this asymmetry, right? And then so what? But however, if we go to the intermediate range between pure ballistic and fully diffusive, and we know actually the conductivity we can write in this way, this empirical formula. Lambda is the mean free path. L is the size of the device. If lambda is huge, we recover this ballistic limit. If lambda is very small, we recover the Ohm's law. Yeah, the conductance is inverse to the resistance to the length of the device. But if we assume a finite relaxation time tau, then we require the velocity. Here, the velocity play a role. If we ask a question, if the electron go to the right, then is the right moving velocity come here. If electron come to the left, then the left moving velocity play the role. Yeah. In this sense, we get a feeling. Actually, the total conductance for a finite size system will depend on the velocity, will depend on the moving direction. Use this very simple formula. Let's go a little more, like let's just write down the resistance. This is the like the magnetic resistance definition, the change of resistance over the total resistance. We can write it. We do a little mathematic, and then this is the difference between left moving and right moving electron. And this is the total velocity. This is related with the geometry. But if we assume this eta term, all the L go to infinite, this means the lifetime is very short and the device is very long. This is a strong scattering region, and we get this limit. Actually, this limit is nothing like this velocity is proportional to the density state. Then in this way, we see immediately if the density state is huge, or if we have a flat band, like twist bilayer graphene, this UMR, this term will be large. And this is the motivation we go to twist bilayer graphene. And shortly also because the starting point is twist bilayer graphene breaking invariant symmetry. Now, let's see the numerics. What we do is simply we start with the twist bilayer graphene, and we apply in-plane magnetic field. And in this case, because for the way in-plane magnetic field, we cannot use the continuum model. We use the tight banding model plus the magnetic field. And with the finite magnetic field, the band structure will change. This is the band structure before, with or without magnetic field. You see the left and the right are slightly different. And this is the density state of this band structure, nothing more. Then this is the MR, the magnetic resistance change. And you see here, actually, when the density state go to the peak, we have the huge MR enhancement. And the change of the resistance or conductivity is about 20%. And well, by the way, this change is like we calculate the conductivity difference between the left moving and the right moving. We simply flip the current direction. Well, for this model, we can check many twist angles. And like at a different twist angle, indeed, as we reduce the twist angle, and this UMR change, like I remind you, this is the log scale. It's changed quickly. And it's scaled very well with the densil state. With the densil state, the peak of this densil state. By the way, so far, all this calculation is based on this non-interacting band structure. And the basic information is the Fermi velocity. Actually, it's pointed out, actually, this UMR, when it's combined with the superconductivity, and this phenomena can be huge. And considering the interesting superconductivity in TBG, I outlook possibly when this phenomena connected with the superconductivity experiment, this could be give us something new. And well, in the end, let's see about the nonlinear anomalous Hall effect. And this nonlinear anomalous Hall recently experimented already mirrored and realized in tungsten ditelluride. And beautiful in theory is Liang Fu and N.T. Solomon. They derive it actually. This nonlinear connectivity is related with the Barry curvature dipole in the band structure. Like although it still depends on relaxation time tau, but it's directly related with the intrinsic quantity from the band structure, and just like the anomalous Hall effect. And then in this way, this is making it very intuitive to find which material could give us huge nonlinear Hall. And then just from this, it motivates us to think about why a semimetal, because this is singularity point of the Barry curvature. It must has huge dipole. And therefore, why a semimetal and tungsten ditelluride attracted our attention immediately. And also, well, kind of for why semimetal, we assume strong Semimeltal coupling. And then there's an interesting question. To realize this nonlinear anomalous Hall, do we always need a strong Semimeltal coupling, always need wire semimetal? Sure, not always wire semimetal, not necessary, right? And anything else with a strong Barry curvature, that's enough. In other words, strong Barry curvature also not related with not always depends on SOC. Some material without SOC, we can also realize huge Barry curvature. Then one way is this flat band system. And we go back to the twist bilayer fan gap. And in this case, here this is the band structure. By the way, in this case, we have to, for twist bilayer fan, we have to break the C3 rotation symmetry. Otherwise, nonlinear anomalous Hall disappear. This Barry dipole disappear. And numerically, we calculated this Barry dipole is proportional to the nonlinear conductivity. And we get a big value for reference tungsten ditelluride layer. This value is in the order of 10 here. We get 1 order of magnitude huge. Then here, now, possibly, I think today we have a lot of like TBG experiments. What people can do is just use the older device directly mirror this Hall signal out to the second harmonic. In the end, I acknowledge my collaborators. The nonlinear anomalous Hall work is collaborated with Vic Law from Hong Kong, and also thank the group members, Daniel, Tobias, Izhou, and Jae-Wen, and thank ERC funding. And overall, this is a summary. In twist bilayer fan, we can realize this huge shift current, and also in the transport measurements, I simply propose if you mirror the transverse voltage, you will get a nonlinear anomalous Hall. There's another one if you mirror the longitudinal voltage, but to the second harmonic. This is the UMR effect. This is the non-reciprocal or transport. With that, I thank you for your attention.
Okay, so okay, yeah. So I'm gonna thank the organizers also for this fantastic workshop. I think it's a great collection of talks. I'm learning a lot. And I want to contribute to the discussion, again, going back to or link to what Liang Wu is telling us about, and kind of give a perspective on what are the hopes of finding quantization in a nonlinear observable, in this case, an optical observable. And so I'm going to talk about the circular photogalvanic effect, we have heard quite a lot about it already. But I'm also going to try to propose a different experiment that gives us a bit of an edge to overcome some of the challenges that experiments might be facing. So I was very happy to hear that this actually blended in quite well with the scope of the workshop. So yesterday we had an introduction, and in that introduction exactly this question came up, and also the role of scattering, which is very central to my talk. So now, even though we've heard a lot of introductions, I still want to kind of put this talk on the map of nonlinear optics. And we were talking about quantization, and of course, in already a linear response, we know a perfect example of quantization, which is the quantum Hall effect. And in the quantum Hall effect, we measure a current proportional to electric field. It's quantized in E squared over H. It's protected. It's an insulator, and this can also be measured optically. Actually, Liang Wu, in fact, reported the observation of this quantization in the surface of topological insulators and their magnetic field. So even optically, you can see this nice quantization. Now, this raises the question of whether we could observe such quantizations, meaning responses that only depend on fundamental constants in nonlinear responses, and also whether we could observe it in metals or not. And if you go to nonlinear effects, then the first non-trivial order is the second order. So for that, you need to break inversion because, well, the current is odd under inversion, while square of electric field is even. So the material itself has to break inversion to make this equation possible. Now, when you do this, you either have a second harmonic generation where these two electric fields interfere constructively, let's say, or when they interfere destructively, you have the intrinsic photogalvanic effect. So this has been already a subject of many talks. Of course, if we go to higher order, we also have very nice physics in higher harmonics, as we heard yesterday. But I'm going to focus on this photogalvanic effect. Now, depending on polarization, you have different phenomenology. Also, we heard about this. And in the particular case, we have time reversal symmetry. This we usually call shift and injection current. They actually are generated by these polarizations. And shift is just, as Takahiro is explaining, is a constant current, while injection is rate of change of current. And it is that together with other colleagues, we suggested could be a candidate for quantization in nonlinear optics. And the difference here is that this quantization is going to be not in units of E squared over H, but in units of E cubed over E squared. And also it's going to be relevant for metals rather than insulators. So the question arises, like, how robust is this, and can we actually observe it in experiment, which is actually the question I want to address in this talk. Now, we basically want to go from perhaps known and practical and kind of beloved linearity to kind of more interesting grounds and perhaps even more beautiful. But we have to ask ourselves how much can we stretch this in reality. So first, I'm going to start kind of increasing complexity as I go along. So first, I want to explain where we could expect to see this. So we need chiral topological metals. Where is this? So topological metals are metals where there are band crossings with a certain invariant, which is essentially the integral of the Berry curvature in momentum space, as we all know. And in most metals, most topological metals, the problem is that these two, because of time reversal symmetry and usually mirrors, these two chiralities appear at the same energy. So if you optically excite one, you will optically excite the other one. And if you have a response that depends on C, it would cancel out to 0. In chiral topological metals, by definition, you break all these mirrors. And so you can access one node without really optically activating the other, and this gives us hope that we can measure this quantization. So yeah, so this is the point I'm trying to make here, that if the Weyl nodes are at different energies, which you achieve by breaking all mirrors, then only one single Weyl node is optically active. Now, what is actually quantized? So it turns out it's the injection current, or part of the injection current, that is quantized. So the injection current, as I said before, is the part that actually flips sign depending on the polarization. So you can write this as this E cross E star, which you'll see sometimes in my talk. And now you have to, you want a rate of change of current. So basically, you're looking for poles of this quantity, which so poles just mean 1 over omega. If I pass the 1 over omega over, then in the time domain, this is dj dt. And so depending on the frequency of the incident pulse, it will tell, there's a response coefficient, which we call beta, that tells you where is the current moving, or the rate of change of current moving respective to the polarization plane. And what we found is basically that if you take the longitudinal part, which means taking the trace of this object, then this is exactly measuring the integral over the Berry curvature of one of the bands over a surface of optically activated momenta. So you shine light, you have some optical transitions, this define a surface in momentum space. And if this surface encloses just one node, then you'll get C, and this is quantized. However, this unfortunately is only exact for 2-band models. That's why I can only refer to one of the Berry curvatures. And the name of the game is how do other real life perturbations change this result, and whether we can outsmart nature to measure this. And so notice that it's a longitudinal current. So the current is actually has to be measured along the propagation of the light source, or perpendicular to plane of polarization. Now, in the 2-band limit, let me just explain what you would expect. So imagine I have this material which is doesn't exist, or at least only exists in crystalline form in the minds of theorists, but it's quite nice because it has this 2 Weyl nodes here. So let me forget about all these bands and focus on this 2-band model. And now what you will see, if you measure this trace of beta, you would see that basically at low frequencies, it's activated because it's polyblocked. And then at some energy, you would activate the node and measure some universal response. And this will last until the other node gets activated. So a non-universal region in frequency, and then it will cancel out and eventually die out to 0. So the region where you observe actually depends on the separation between the Weyl nodes, as I was explaining, and you want to maximize this as much as possible. Now in real world, again, we have many bands, and in fact, it's relatively simple to show that if you have bands that are separated from the Weyl bands by a distance in energy of delta E squared, then you'll get a correction of omega squared over this quantity. And so that means that if they're very far away, this correction can be made small, but in general, if it's close, then it cannot. So now it becomes the reality check for theorists. So what do we have in reality? So in reality, materials have more than 1 band. So I don't have to tell you this, but more than 2 bands. So then we have to be careful. And so here I write the correction that I was telling you about with an extra matrix element. And the reason is that, in fact, we thought that when you have multifold nodes, which are crossings that of multiple bands crossing at a single point, which can have higher return numbers, also can be beneficial to observe this quantization. These corrections would kind of diverge because this delta E is very small and make quantization unobservable. However, Chang et al. Came along and suggested that rhodium silicon could be a nice material to look at this at, and they noticed that when they calculated the CPG, this injection current, they noticed that the plateau survived. And so, and it was basically coming from this multifold nodes. And so that was quite puzzling for us because of this. And what ends up happening is that in fact the nice symmetries around the gamma point make the matrix elements vanish, and so the corrections actually vanish if you are very close to the gamma point. And so we classify basically all Hamiltonians that look like this, so some spin matrix or equivalent of spin matrix times k, and we kind of suggested that these multifolds always have a region, sometimes small, where you can observe quantization. And now the game is how small is the region and where can you observe it. But in general, multiple bands will correct quantization, and we shouldn't hope for precise exact quantization. And the Chern number in this case could be sums of Chern numbers of different bands. So then we went along and calculated a die binding model for rhodium silicon. And indeed, the value is close to quantization. With spin-orbit coupling, this degeneracy is kind of lift, but you still have multifold crossings that are a bit more complicated, and they give you kind of more sizable corrections. But nonetheless, it's quite close to, it would be expected to see something close to quantization. However, we have in reality another problem, which is disorder. So as I was explaining before, this is a rate of change of current, which we're measuring. And so this complicates things in the following way, because if you are trying to make, to find this quantized coefficient, you're trying to measure this quantized slope in a time that is shorter than the typical scattering time in your material, which could be as short as a femtosecond, I'm not sure if you, depending on the material, but and later on, if you're just too slow, then this current will saturate and give you some non-universal coefficient that depends on the scattering time times the universal value. And so if you're in this region, then you're bound to, you're basically forced to estimate this tau and try to come up with C after estimating tau. So this is the summary of these two kind of challenges we're facing. So in fact, you need materials where this matrix elements are small so that you can forbid this type of corrections. So rhodium silicon and cobalt silicon, as I'll show later, seem to be good in this respect. Then you would like materials that are clean enough so that this is long enough so that you can, your scattering times are longer than the pulse width to avoid this universal result. And yet there's a third challenge with, it's kind of less known for the moment, but it's quite interesting as well, which is electron interactions. And in this respect, you can, it was shown by Joel Moore group, that if you add interaction corrections, just as like if you were around with the story of the universal conductivity of graphene, is a similar story. You add interaction corrections, that you get a correction to this quantized value that depends on different things like the screening wave vector or the chemical potential. And now it turns out that, okay, this F depends on the interaction you put, but let's say for Coulomb interactions, you actually can reduce it if you have strong screening. But in general, if you're close, for example, to a vial point, for example, this might not be small. So this you have to also consider. And let me just put a side note here that if you have, it turns out that if you have exotic interactions, you can, some models with exotic interactions, you can actually map through some sort of quantum field theory duality to a non-interacting system. And those models don't have corrections, but unfortunately they're not very realistic. So you're stuck with these things, and now you have to come up with solutions to them. So for the materials, we seem to have more or less the right ones, rhodium silicon and cobalt silicon, although it would be nice to have a chiral vial which is just two vials at the different energies and well separated in energy, but this seems not to exist in nature, at least as far as I know. And these materials unfortunately have relatively short scattering times, so we have to kind of find a way of estimating the scattering time or do something smart. And try to live with the fact that some interaction correction might be present, or try to find materials that are like heavily screened. So what's the experimental status? You already heard a lot about this in Liang's talk, but I'm just gonna summarize it with this perspective, comparing rhodium silicon and cobalt silicon. So these are two band structures. They're in the same space group. So you see these two nodes, a 3-fold and a 4-fold that might be split with spin over recoupling. But let me just simplify the discussion for the time being. And so the dispersions basically look exactly the same, except that the energy scales that basically have in cobalt silicon. So so this is nice. The band structure is relatively simple. You can develop tight binding models, so encapsulate models around these points, or even like a tight binding model that captures a lot of the features of these few bands at Fermi energy. So that's quite nice. Electron interactions are kind of a bit of a mystery at this point, but one could hope that since if the chemical potential is actually below the 3-fold node here, then this large hole pocket might be causing a large screening, and then you might be safe for this type of correction. And the Zor scale, as I was saying, is actually like around 100 milliV or 40 milliV, depending on the material, which is relatively short. Shorter than definitely what we need to observe this nice quantization. Okay, so then how do you estimate tau and actually get a notion of where the chemical potential is? Because it turns out to be quite important. So you look at the linear conductivity, and here in this psychedelic plot, we can see the optical conductivity measured in experiment in orange. And then I wanted you to notice basically that DFT, unless you put a 100 milliV broadening, then you get extra features that you don't really observe in experiment. And this is in fact consistent with tight binding models that we developed that explain the data. If you add the best fit to the data, it always comes with broadenings that are quite large. And in fact, the other important notion is that the chemical potential has to be actually below the 3-fold node, because if not, you wouldn't really explain this little hump here that you can barely see in the experiment. So these are the two things that we learned from this. So now we have a sense of where the chemical potential is and what is the carrier lifetime. And now one could look at the CPG in rhodium silicon. Now the first groups to do this were the Ornstein and so Joe Ornstein in Berkeley and Larry Starczynski in Temple, and they measured something that looks like a quantization. Now they're plotting beta times tau, because you have to estimate tau, as I was saying. The optical conductivity is also very broad, and this is interesting because we had a DFT, or Yang Zhang calculated a very nice DFT results that if you look at the coefficient with spin-orbit coupling, actually kind of resembles this curve. We don't really know why, because one would think that the chemical potential is below the node, but this is what seems to be better agreeing in this experiment. If you compare to what Liang measured, actually, this is a bit different. It agrees better with the chemical potential below the node. And you can see that DFT kind of captures quite well the peak and the sign change. The tight binding, we know that is quite bad at energies that are higher than 0.4 basically. And nevertheless, at least to capture the overall order of magnitude and the position of the peak, but nevertheless the shape is relatively consistent with DFT. So, one possible explanation is the samples might have different chemical doping, or this might be unlikely. And as well, there's the fact that to calculate this CPG, actually, we assumed a constant scattering time that might otherwise be dependent on frequency. So this we don't know. So, but in fact, you're quite constrained. It is you would expect that one interesting thing is that to plot this type of plots, you actually have to kind of match the broadening and the peak height. So the broadening, both the broadening and the peak height depend on tau. So you're a bit constrained in which tau you can choose, and they have to match also the linear optical conductivity. So this is I would say interesting that with the same parameters you can basically fit both. So that's kind of reassuring in this sample. And now in cobalt silicon, the story is a bit better, because the conductivity, even though it still looks relatively broad, is quite interesting to examine the low energy regime, and we have done this in one of the papers. But we kind of understand again the same ideas we can apply to this material, and you can see that now there's again another hump. Which is slightly closer to 4, which is the quantization expected for this or this, I should say, node, because well, these guys have churn number 2 times spin is 4, so you would expect a quantization of 4. However, as you can see, it's not really there, and this was taken at 300 Kelvin room temperature. So quantization is closer, but it's not really there. One option is to change the chemical potential, as Liang was mentioning. For example, you can move it up to see the quantization of the fermion at gamma, but the samples right now seem to have the chemical potential below. This also kind of explains the sign change, and it can be also captured by a low energy K2P model, as well as the type binding. So cobalt silicon is promising, but not quite there yet. So we either have to figure out how to dope it or come up with a different experiment altogether, because the scattering time is still too short to observe quantization. Maybe cleaner samples would be also nice. So we came up with a different alternative, which I think it's quite interesting, not only because it can allow to circumvent some of the problems, but also gives you some other information about the material you're probing, which is difference frequency generation. So in this map that I was showing before, it wasn't there because now you need 2 laser pulses, omega-1 and omega-2, and in a nonlinear material without inversion, you would expect their respective second harmonic generation. There's some frequency generation, so omega-1 plus omega-2, but also their difference frequency generation. And the photogalvanic effect is basically a monochromatic limit of this. So now you have 2 frequencies. If you make them the same, you're back to the story I was just saying. If you have them to be different, then you have another knob to outsmart scattering, which is the idea behind this. So how do you do this? What we propose is to tune this difference in such a way that it is kind of in the middle of 2 scales. One is the sum of the frequencies. So omega-1 plus omega-2 is right here, omega. Then delta omega is here, so omega-1 minus omega-2. And those are much bigger than the inverse scattering, much bigger than the scattering rate. So if you're in this regime, and I'll explain how you can achieve this in experiment without even knowing what tau is, you would get something like this, which is, again, some circular response. But now you have 2 terms that oscillate out of phase, so with a sine and a cosine. And one of them is exactly the same tensor as I would explain below. So it's the CPG, just the one that's quantized and we would like to measure. But also, kind of for free, you get this extra term that is actually only non-zero for metals. And this term has quite an interesting history dating back to Genkin and Mednis, who first derived it in 68, because it's actually, you can rewrite it as the K derivative of the integrand of the reactive part of the linear conductivity. So you take your linear conductivity and you do something to it. Namely, you take the Fermi function. It amounts to taking the Fermi function and substituting it for the derivative of the Fermi function over omega. So the derivative of the Fermi function is peaked at the Fermi surface. So this means that this is a Fermi surface term. So you know that in the linear conductivity, there's a term that tells you what is the Hall effect, or the optical Hall effect, if you want. And this, if you do the substitution, then immediately you will get the Berry curvature dipole. And this is what was found by Solomon and Fu. Here, remember, we're in the clean limit, so there's no tau. But nonetheless, this is the same contribution. However, there are other parts in this linear conductivity that if you do this, or you actually go through the process of deriving this nonlinear response, you'll find this equation, which has some matrix elements, which I won't comment on. But the important thing is that it actually depends on combinations of bands in such a way that there's this denominator that can blow up whenever you have a transition that is active. And this comma A reminds us that it's a Fermi surface contribution. So it's a Fermi, or should I say a Fermi surface integral. A Fermi surface integral is 0 if you don't have a Fermi surface, but it depends on other bands. So this is quite interesting because now you can calculate it for real materials. And what happens is that, as I was discussing before, this part will give you plateaus, just the same exact curve. But this free carrier will have divergences at the activation frequencies where these nodes actually start contributing. So in this case, you will see that there's these divergences close to where the gamma point activates and where the R point activates. And so this is quite nice because you can already, using this, you can not only tell where the while nodes are being activated, but also measure kind of independently a response that is only non-zero in metals. So the two contributions are out of phase, so they can be measured independently in principle. And you don't really need to know what the scattering time is. You just kind of fix the frequency and start changing delta omega. And when you reach the right limit, you will see basically peaks or divergences that appear in the in-phase component. And so you can do this actually in non-chiral materials like tantalum arsenide. Here now the difference is that you have to look at other components that are non-zero, like some transverse component, for example. You'll find this beta and some other peaks where the vial nodes reside. So it's actually, I would say, an interesting experiment just simply to know what the band structure is, and then later on observe quantization. And notice that here you don't need to know what the scattering time is, which is kind of the advantage. So just to sum up, I've kind of summarized the question of is nonlinear quantization observable into 3 parts. So one is the material choice. We have relatively good materials like cobalt silicon, which is a cleaner candidate rhodium silicon, as we showed. We still lack a clean chiral metal, which is what I mean by a chiral metal is something that looks like this. It would be very nice if somebody could grow it or predict it. And the short scattering time problem you can circumvent by looking at DFG, so difference frequency generation, in the appropriate limit where the sum of the frequencies is the largest scale, the difference is the intermediate scale, and the scattering time or the scattering rate is the smallest scale, which we think is achievable in experiments, given the large separation of vial nodes in cobalt silicon and rhodium silicon. And then interactions, I mentioned this result by Joe Moore's group that large screening is helpful, and also a bit of some hope that could be that there are either theories or other nonlinear effects that could be protected from interaction corrections. And then I want to also kind of reemphasize the point that it was already made yesterday, that maybe there are other quantized geometrical responses that we have missed, and it would be very nice to predict and observe. So with that, I'm going to thank all the people that have contributed to this kind of large amount of knowledge, especially Fernando Juan and Miguel Angel, Charé, and all the experimentalists, Darius and Liang and Joe, which I don't have a picture, unfortunately, of. And with that, I'll take any questions that you have. Thank you.
So, so I'm going to describe some kind of old work and some recent developments in this direction. It's centered around nonlinear Hall effect and how that might be useful for terahertz technology. So, yeah, the general picture is that in electronics we study low frequency electrical transport, and we know that there are all kinds of topological contributions to quantum transport. And now, on the other hand, in optics, we think about shining light on quantum materials and study their response. So take-home message is that if we think about terahertz response, when the frequency is small compared to the relaxation time, and when the electric field strength is small. Then there's a direct connection between topological transport and the terahertz optoelectronics. Okay, so this work started about 6 years ago together with Inti Soderman, and later works were done in collaboration with Michal Paja, my student, Hiroki Isobe, and Yang Zhang, who is a current postdoc in my group. And great fortune to work with brilliant experimentalists, Chong Ma and Suyang Xu. And it's really their beautiful experiments in the lab of Pablo and New that got this field going forward on this nonlinear Hall effect. Okay, so let me very quickly review the anomalous Hall effect. This occurs in ferromagnetic metals. Even when the external magnetic field is 0, there's a non-zero Hall resistivity, and that's proportional to the magnetization. An important contribution to this anomalous Hall effect comes from the so-called anomalous velocity. Again, it was studied for decades. The general idea is that if you consider a block electron wave packet in a crystal, then the wave function has both an intra-unit cell part and a envelope wave function, right? So usually we think about the velocity associated with the envelope function, the center of mass of the wave packet. However, as an electron is accelerated, the intra-unit part of the wave function also changes, and that gives an additional current, gives rise to an additional velocity. So this is a velocity that is linearly proportional to the rate of change of the momentum. So that's anomalous. And as you all know, that this anomalous velocity is directly proportional to the barrier curvature. It's basically a cross product of the barrier curvature and the rate of change of the momentum. And the barrier curvature is an intrinsic quantity, only depends on the electron wave function in momentum space. It's really a measure of quantum geometry. So in linear response theory, when we look at the current associated with anomalous velocity, we are supposed to take the anomalous velocity sum over all the occupied states. Because the anomalous velocity is already proportional to the electric field, which is gives the rate of acceleration for the wave packet. To the linear response level, then we need to just use the equilibrium distribution function. And this gives us the formula for the anomalous Hall velocity. It's an integral of barrier curvature over all the occupied states in the thermal equilibrium. And for time reversal invariant systems, we know that the energy dispersion is symmetric and the barrier curvature is anti-symmetric in K space. So this means that the integral has to vanish. The time reversal invariant system does not have any Hall response at a linear response level. So on the other hand, many materials that we are interested in nowadays, including bilayer graphene, generally graphene systems, including transition metal diacarbonides, including wild Semimetals. All these materials have a common feature that inversion symmetry is broken, but time reversal symmetry is present. So in this case, a barrier curvature can still be present in momentum space, but it is guaranteed that at momentum k and minus k, the barrier curvature would be opposite. So if we take a integral of barrier curvature over all the occupied states in equilibrium, then the integral vanishes. Now, what if we go beyond the thermal equilibrium? If we go beyond the linear response? So consider, for example, when we apply an electric field, we know that we will obtain a current carrying state. And in this current carrying state, the Fermi surface is displaced in momentum space. So the occupation of states at k and minus k will be unequal. And when we use this displaced distribution function in the expression for the anomalous current, then we immediately obtain a Hall current that is proportional to second order of the applied electric field. The change of the distribution function from equilibrium is first order in electric field, And in the diffusive system, it's simply given by this expression here. It's proportional to the scattering time tau, proportional to the electric field. It involves the spatial derivative of the Fermi-Dirac distribution with respect to k. And then the anomalous velocity is given by the barrier curvature in cross product with electric field. So finally, we get this expression, which is very simple. It's basically when an electric field is applied, then to second order in electric field, there generally would be a transverse current. It's always perpendicular to the direction of the applied electric field, and it's given by a Joule-like prefactor involving the scattering time tau, but then it involves the barrier curvature, right? It involves barrier curvature instead of the other quantities like the electron mass or electron density. Okay, so this relation, right? The transverse current depending quadratically on the voltage, this can be thought of as a diode. This nonlinear IV characteristic immediately implies that if we have a slowly time-dependent input voltage, for example, a voltage that oscillates as cosine omega t, then when omega is very, very small, let's say on the order of 1 hertz, 2 or 10 hertz, and then when the current in the transverse direction is simply given by the instantaneous current, at any instant of time, there is a voltage that's being applied, and that generates a corresponding voltage. So as the input voltage varies, the transverse current would vary with it. So that's why the cosine omega t time dependence of the input signal will create an output current in the transverse direction, which depends on time as cosine squared omega t. It all comes from this intrinsic quadratic current voltage characteristic. Okay, so this is what I mean by a quantum diode. We're not talking about any PN junctions. Just sending current, applying a voltage to a homogeneous quantum material with barrier curvature dipole, then a transverse current would develop with both 0 frequency component and the 2 omega component. So, so now one can ask, whether this relation extends to higher frequency. And again, as long as interband transition is not involved, as long as frequency is small compared to the threshold for interband transition, then within the Boltzmann transport theory, one can show that the second order response, it involves a Joule-like frequency dependence, and it's directly proportional to this quantity, which we call barrier curvature dipole. It's integrated over all the occupied states in equilibrium. Okay, so in two-dimensional systems, this barrier curvature dipole has a unit of length. It's allowed in inversion breaking materials with certain symmetry point groups. And in two dimension in particular, this barrier curvature dipole is only allowed when the system has a polar axis. And in that case, when applying electric field perpendicular to the polar axis, a transverse current will be developed parallel to the polar axis. So symmetry allows this kind of a second order response. And one way of obtaining this barrier curvature dipole is from tilted Dirac fermion in two dimension with a mass. The mass of Dirac fermion creates barrier curvature, while tilt provides a direction that captures this polar axis. And this is how the minimum model for the barrier curvature dipole. And so Chong will tell you more about this exciting experiments she and Su Yang did on bilayer tungsten ditelluride. And in this system, again, because of the band inversion, spin orbit coupling, and this layer structural asymmetry, a barrier curvature dipole develops both at the bottom of the conduction and the valence band. And the barrier curvature dipole has the same sign. Okay, so so this is the experiments. You see that a quadratic current voltage relation, and it's only present when the voltage at the frequency 2 omega is measured in the transverse direction. So this is the first discovery of the nonlinear Hall effect in any solid. Okay, now in addition to this barrier curvature dipole, there are additional contributions to this second order response that has to do with disorder scattering. in particular involving side jumps and skew scatterings. And I won't go into detail, and just to show that, yeah. Okay, so now because of all these complications associated with disorder, so this motivated us to study whether nonlinear Hall effect can occur in ballistic devices without any scattering. Okay, so this is the kind of the device we have in mind. There's a source and drain. We can bias it so to supply a current carrying state, to create a current carrying state. And then the question is that will there be a transverse current in response to the source drain bias voltage difference? Okay, so so in this case, because disorder in the ballistic regime, so the only contribution to this transverse current has to come from the barrier curvature, and barrier curvature is directly related to the intrinsic chirality of the electron wave packet. So you can think of this as analogous to the so-called Magnus effect, right? So if you have a rotating ball moving against the wind, it will deflect sideways. Here, likewise, an electron is intrinsically circulating on the atomic scale. The electron wave packet generally is self-rotating. Okay, in inversion breaking crystals, electron wave function is intrinsically self-rotating, and this kind of a self-rotating electron wave packet moving against a potential gradient, and that experiences then a side force, pushes this electron wave function to the side. Okay, so for that reason, we call this nonlinear Hall effect in ballistic systems the Magnus Hall effect. Okay, so now again, if we want to calculate the current in the transverse direction, we again use the distribution function of the electron multiplied by the anomalous velocity. The only difference with the diffusive case is that the distribution function is different. So in ballistic systems, the distribution function is determined in the following way. All the right moving electrons are filled up to the chemical potential mu L of the left reservoir. All the left moving electrons are filled up to the chemical potential of the right reservoir. Okay, so with this simple result, then we find that the anomalous current in the transverse direction is proportional to the chemical potential difference between the source and drain. It also depends on the potential gradient inside this region. Okay, but in the end, I'm not going into the details. In the end, if you integrate all the current density in the y direction, the total current is only depending on the chemical potential difference between the left and right reservoir. Okay, because the chemical potential difference is also the electrostatic potential difference. So, so this then leads to this formula for the ballistic nonlinear Hall effect. The transverse current is proportional to the source drain bias squared, proportional to this quantity, which is the barrier curvature now integrated over all the electrons that has a positive velocity in the x direction. So x is the direction between the source and drain. So, so in other words, this quantity does not involve any disorder scattering, does not involve any relaxation rate. It's purely determined by barrier curvature of instant electrons on half of the Fermi surface, right? So if you think about the entire Fermi surface, half of the electrons are moving to the right, half are moving to the left. So then we take all the right moving electrons, those states, and integrate the barrier curvature, and that will give us the transverse second order current. Okay, so when you reverse the source drain bias, both the chemical potential difference changes sign. So instead of having an excess amount of electron moving from left to right, now we have an excess amount of electrons moving from right to left. And at the same time, the electrostatic potential gradient also changes sign. So that's why the 2 minus give a plus. So when we reverse the source drain bias, the transverse current is in the same direction. So this is the second order response. So, so we proposed in this work with my student Michal that bilayer graphene under electric field may be a good system to look for this nonlinear Hall effect in the ballistic regime. And because of the, when you apply electric field, a gap develops in graphene, in bilayer graphene, and this creates barrier curvature. And because of the trigonal warping, it creates a non-zero integrand here. The integrand would vanish in the absence of trigonal warping, but it's non-zero in the presence of trigonal warping. So basically, the two valleys have opposite barrier curvature, but they also have opposite trigonal warping. So that's why the integral is non-zero. There should be a non-zero transverse current. Also, I want to emphasize that in this case, this system bilinear graphene has 3-4 rotation symmetry, so barrier curvature dipole is guaranteed to be absent. While in our formula for the ballistic nonlinear Hall effect, it's still finite. Okay, so this is a good way of distinguishing ballistic versus diffusive systems. Okay, so how much time do I have? Let's see.
You have 10 minutes.
Oh, perfect. Yeah, okay, then it's perfect. So let me now move on to go beyond the low frequency response, talking about the connection to terahertz physics. So again, first let me compare the case of two kinds of a nonlinear device, right? A diode, a PN junction, or a Schottky diode, a metal semiconductor junction, is a canonical example of a nonlinear device. It has a nonlinear IV characteristics, and in this case, we know that this provides rectification when you pass an AC input signal can be converted into a DC, an output signal. But for this to work, the input voltage has to be above a minimum threshold. It's called a forward voltage, because at very small input voltage, the IV characteristic is always linear. And also, the input voltage cannot be too big, because otherwise, current will conduct in the opposite direction. So the voltage has to be in between the forward voltage and the backward voltage, breakdown voltage. And that is one limitation of the diode. And also, because electrons has to go through some kind of a barrier or some kind of interface, there's an intrinsic transit time limiting the operation frequency. So that's why it's very difficult for Schottky diodes to operate efficiently at frequency above 1 terahertz. Okay? So on the other hand, we see that for this kind of a nonlinear Hall effect, the IV characteristics is intrinsically quadratic. Okay? Because in the transverse direction, there's no linear response current. And because of the nonlinear Hall effect, there is a quadratic current. And so this means that for this rectification process, it can operate without any external bias. So any small amount of input voltage will be converted into a DC output current. And because electrons move through a homogeneous quantum material, it can operate at very high frequency, only limited by the scattering rate. Right? The scattering rate in a typical material is usually at least 10 terahertz at room temperature. So this shows that, gives us some kind of a confidence that this nonlinear Hall effect can be used to rectify signals up to terahertz or 10 terahertz frequency. And also, this terahertz range is also inaccessible by conventional photonic devices. And for example, the photodiodes, again, I can provide by absorb a photon to create a current, but this cannot work when the photon energy is below the band gap. So the terahertz frequency is in between the electronics that operate at very low frequency, like a few gigahertz up to 10 gigahertz, let's say, and it's also far below traditional photonics. So there's the so-called terahertz gap, and this nonlinear Hall effect we think it has is promising for filling this terahertz gap for the reasons I described. That this effect is based on the intrinsic nonlinear quadratic IV characteristic of a quantum material, and the operation frequency is only limited by the scattering rate. So, terahertz has a lot of applications. For example, because it can penetrate through many materials, it can be is widely used for security checks. And so this led us to propose in this work with Yang Zhang a long wavelength photo detector. So when we have a terahertz source, we can use antennas to focus the terahertz field into a small quantum material region. And this quantum material, when it has a large nonlinear Hall effect, it'll convert the terahertz field into a DC current in the transverse direction, which can be measured for detection. Now, an important technology parameter for a detector is the so-called responsivity. It's the current responsivity is defined as the current divided by the instant optical power. And when we have a good impedance match, then the absorbed power would be given essentially by the conductivity times E squared. All these are basically associated with Joule heating of the quantum material. And while the transverse current, the DC output photo current is proportional to the nonlinear Hall conductivity. So now both the nonlinear Hall conductivity and the linear response conductivity involve the same Joule prefactor, right? The same Joule prefactor, so they cancel out. So finally, this means that the intrinsic current responsivity is an entirely intrinsic material parameter, depends only on the Barry curvature dipole, on the effective mass at the Fermi level, and depend on electron density. So this essentially the Joule prefactor. So this new result essentially is that the intrinsic current responsivity is basically the Barry curvature dipole divided by the Joule weight. So these are all intrinsic material parameters. So we can use a DFT to calculate and to find the best material for photo detector. So the material we identified is niobium phosphorus. This is a wild semimetal in the same family as tandem arsenic. But unlike tandem arsenic, it has the Barry curvature is concentrated not just at the wild point, but actually is concentrated near a nodal loop. Essentially in this system, to zeroth order approximation, because of the band inversion, the conduction and valence bands, they cross each other on a ring, and then a small spin orbit coupling gaps the ring, every point on the ring except two wild points. But the Barry curvature is really concentrated near the ring, not at the point. So, so we find, using this formula that is shown, we find that this responsivity is in the range between 1 and 0.1 ampere per watts for a device size between 100 nanometers to about 1 micron. And this, importantly, this responsivity is also frequency independent. So it should operate efficiently over a wide range of frequencies up to the scattering rate, which is about 10 terahertz in this material. So, so we expect then our proposal then is that this niobium phosphorus can be a useful photo detector at low wavelengths. It has a fast response. It works in a very broad range of frequencies. It has high sensitivity, and because this detection scheme does not involve any external bias, it operates in a self-power mode. Okay, so finally, I also want to highlight this very recent experiment on platinum telluride. This is another topological semimetal, and in this case, in this experiment, the authors actually made a terahertz detector out of it, and you can see that you can use this to take terahertz images at the room temperature. And the responsivity is actually quite good. It's in the range between 0.2 to, without external bias, it's 0.2 ampere per watts, and the noise equivalent power is 2 picowatts per square root of hertz. Now in this material, it has a 3-4 rotation symmetry. So we believe that the nonlinear response actually comes from the surface states due to the scattering mechanism. And that is hard to predict, but we think that with this Barry curvature dipole, the effect can be even larger, and the niobium phosphorus seems to be a good candidate. So yeah, so I'll basically end here. So essentially, over the sort of many decades, all kinds of Hall effect has been studied, and perhaps now with the nonlinear Hall effect can actually be useful for some developing new quantum technology. Thank you.
Oh, thank you. Yes, I'm Chris Weber, and the work I'm going to tell you about was done with a lot of talented undergraduate researchers. and also with some really wonderful collaborators. So the people in green did theoretical calculations. The ones in red have helped to make and characterize the samples we measure, and the people in blue have helped us with some of these measurements. Now, I'm going to talk to you about ultrafast control of Dirac electrons. And so I guess I should spend a few minutes on telling you what I mean by that and why I think it would be a good thing to achieve. I'm going to move on after that to tell you just a little bit of well-known physics about the Peierls distortion that will be relevant to this talk. And then I'll get into my own favorite material, strontium manganese antimony 2. And in this material, we think that an oscillation of a coherent phonon might be able to actually periodically open and close a gap at the Dirac node. I'll then put this into context with a few other materials in which similar physics, but certainly not the same physics, is thought to be in play. And finally, tell you what we still need to learn about this effect in strontium manganese antimony 2. And spoiler alert, as they say, I am not going to end the talk by telling you that we have definitive proof that this actually happens. I'm going to end it by convincing you that there are good odds that it is, and that it can happen, and that we can actually demonstrate it. But there's a lot of work left to do. Now, my own work that's discussed in this talk is mostly discussed in that PhysRevB article cited at the bottom of your screen. For bigger picture things, you might want to look at a perspective article that I'll be publishing hopefully in a few weeks or so in Journal of Applied Physics. That one is more generally on ultrafast phenomena in Dirac and Weil semimetals. And though, of course, many of you are experts and don't need to read that, I wrote it with beginning graduate students and new postdocs in mind. So if you have anyone in your group who is in those situations, you might want to pass it on to them. Okay, so ultrafast control of Dirac electrons. Why would we want to do that? Well, let's take one step back and talk about why do optics of Dirac and Weil semimetals in the first place. Well, if you do optics, what you know is that it's generally a bulk probe, although certainly some nonlinear optical effects can be surface sensitive. So it's really nice that the 3D Dirac and Weil semimetals have this linear Dirac dispersion throughout their bulk. That makes them easy to study in optics, and it gives them all sorts of interesting optical properties that you might want to study. If you're willing to count ones that have been predicted as well as ones that have been observed, there are dozens. I'll just highlight two that I happen to have pretty pictures of. One that we've discussed a lot is that if you shine circularly polarized light on a Weil semimetal, you get a spin polarized or chiral photocurrent. There's a lot of subtlety to this phenomenon, which you've heard discussed and which is discussed in that perspective article I mentioned as well. Another one that's gotten a little less notice and I think is just beautiful is this prediction of resonant transparency. Ordinarily, if you put material in a magnetic field, then you get resonant absorption at the cyclotron frequency and its harmonics. But if that material is a thin slab of Dirac or Weil semimetal, the cyclotron orbits can't be completed on either surface alone. And so while on one surface, the orbiting electron absorbs a photon, on the other surface, it re-emits that photon, making it transparent. Now, these are just two examples of how much fun we can try to have with optics with these materials. And this will, of course, motivate doing ultrafast optics on them later. Now, let's talk about controlling a gap at the node. Well, if you were to gap a Dirac semimetal, you could get a weak topological insulator. I call those elusive because while they do exist, there aren't so many known materials that are weak TIs, and so it would be nice to be able to study them in a new way. Also, you could use this as a way of detecting light that is not heavy, dark matter. And this actually is something worth taking seriously now because there's several different predictions by different theory groups, all kind of converging on the idea that these materials, if gapped, might be good for such detection. Now, if you could actually control that gap, go back and forth two ways, then what you would be able to do is turn your exotic optical effects on and off, and that would make them possibly useful and certainly more fun to study. You might be able to make a topological field effect transistor. Now, what I'm especially interested in is being able to go from gapped to ungapped by using a short pulse of light and going back and forth on a sub-picosecond time scale. we could do that, then we would really have on-demand control and study of optical effects. We could study their dynamics as they come and go. We could create states that probably don't have analogs in static materials. And the ways of doing this, just accomplishing this sort of back and forth opening and closing of the gap itself would be interesting in the sense that these physical mechanisms have all sorts of subtleties to them. That sounds vague, but hopefully by the end of the talk, you'll understand at least one such mechanism, which is coherent phonons, and what some of the interesting physical questions about it are. All right, so let's take a trip 30 years back in time. These are our data you're seeing, but they could have been anybody's. It's well known that when you photoexcite bismuth, you get oscillations in the reflectivity like this. And those oscillations represent a coherent phonon, all of the atoms moving in sync with each other. This, it turns out, is intimately tied to the fact that bismuth is Peierls distorted. So here's a 1D cartoon. An undistorted material in 1D would be a simple line of evenly spaced atoms. The Peierls distortion is their tendency to dimerize, to bunch up or form pairs. And that, of course, is in a minimum of the potential energy landscape. That's why it happens. An important thing to notice, though, is that it is not a minimum of the elastic energy of the crystal. The lattice actually does not want to distort, but the valence electrons lower their energy when there's a Peierls distortion. So this is really driven by valence electrons, and that matters because when you photoexcite, you profoundly reshuffle the occupations of electrons and holes, and that changes that potential energy landscape. If you photoexcite with a short pulse, it changes that landscape in a flash. But the atoms are heavy. They can't move their positions in a flash, and so here they are suddenly all realizing that they're unhappy. They're not at their new equilibrium position. So they start to move towards that equilibrium, overshoot, oscillate around it. That's the coherent phonon. And the key thing is that it's caused, more or less caused by the Peierls distortion. Any Peierls distorted material is very easy to excite with coherent phonons like this. So the idea now in our material will be this. Since the band structure of the material depends sensitively on the positions of the atoms, if you move the atoms, the bands move. And this has been seen in a handful of experiments, and it really does tend to be this Bohr-Oppenheimer picture tends to actually work. If you get the bands to move with your coherent phonon in just the right way, maybe you could open and close a gap right at the Dirac node like that. This is a nice simple picture, but it probably seems woefully optimistic. What are the odds that could ever work? Well, what I want to do is show you that there's reason to think that something much like that could work in strontium manganese antimony 2. So here's the material. If it boggles your eyes, you don't have to look at it. The middle panel there is showing the Peierls distortion. If you take a hypothetical tetragonal state and then look at the distortion, that's what the arrows represent. They're exaggerated by a factor of 10 because you couldn't see it otherwise. This is complicated. Every atom moves, but theory has tended to focus on the antimony plane, which in the undistorted state would be a square net, and that would give you Dirac fermions. The distortion turns those squares into kite shapes, and the Dirac fermions are destroyed. And in fact, you can see these are my collaborators' calculations. Undistorted, you see a nice linear band crossing near the Y point. The distorted material, you've opened a gap of around 200 MeV, so pretty big. One nice thing is a big gap like that is maybe easier to study than a small gap. Another nice thing is that this gap is intimately tied to the Peierls distortion, which means that if you could excite a Peierls mode phonon, like the one in bismuth, one that tends to repair the Peierls distortion, if you drive it all the way to the undistorted state, you would have to close that gap. This is still a little bit simpler than what's really happening in this material, but it's on the right track. Now, experimentally, what we did is we wanted to see if we could excite such a phonon. So we did a very simple pump probe experiment, 800 nanometers, an oscillator, not amplified. And it's very easy to excite oscillations. You can see from the beating that there's several frequencies there. There's at least 4 in the Fourier transform, but one of them is by far the most prominent. And that is this one at 4.4 terahertz. It's mode 36 out of a total of 48. This is a complicated material, as you can see from the unit cell. So we identified what this mode is, and you might be wondering, is that the Peierls mode? The answer is no, it is a Peierls mode. Peierls distortion being static doesn't have to correspond to any one eigenstate of vibration. And so it actually corresponds to a linear superposition of 6 different, I think it's 6 phonon modes. But this is one of them. And this one partially repairs the Peierls distortion and is very easy to excite. So then we wonder, well, will this actually close that gap at the Dirac cone? So my theory collaborators did a frozen phonon calculation. You start with the true structure, you move the atoms by some amount in the direction of the phonon of interest. Then you take a snapshot of the band structure. And here is that snapshot for 52 picometers of mode 36. You get the bands crossing again. The crossing is a little sideways, but that doesn't bother anyone in this field. And the closing of that gap is linear with respect to the displacement. So if you could excite this phonon to high enough amplitude, what you'd expect, at least naively, is something like this. The gap just opens and closes periodically, 4.4 times per picosecond. This is nice. It's reversible on-off sub-picosecond control of the gap. That would be great. But you might be thinking on-off control means something better than this, right? Couldn't we make that stop at some point? In fact, I find these animations kind of irritating, so I'd like to make it stop. There we go. So here's what we tried to do. We tried using a second pump pulse to see if we could stop the oscillations. And the results are on the right. The arrows show you when the second pump pulse arrives. And you can see that for subtle differences in the timing of that second pump, we can either amplify the oscillations or suppress them. We don't suppress them all the way to 0 because remember, there's multiple different frequencies oscillating here, and there's no one time that will suppress all of them back down to 0 at the same time. Still, this is pretty good. If we could get this to work at high amplitude, we might be able to demonstrate actual, ultra-fast reversible control of this Dirac gap. So let's put this into context. It's going to be clear in the next section. You're probably already very clear that there's a lot of work to do before this is demonstrated. But let me first tell you how it relates to some other materials. Taking a step back, what is it that causes Dirac fermions in the first place? You need a band inversion in order to get states to cross. If that were the whole story, you would have a line node material like is shown here. But of course, quantum mechanics doesn't like states to be degenerate, so it opens a gap pretty much anywhere unless there's something to protect that crossing. And typically it will be protected by crystal symmetry. You zoom in around those symmetric points. This picture is for graphene. Most of you recognize it. And you see the famous Dirac cones. In other words, there are 2 ingredients here. There's the symmetry protection, and there's the band inversion. Now, symmetry matters also for wild semimetals. One way to get to a wild semimetal is to take a Dirac semimetal and break time reversal or inversion symmetry. The wild points will split in K-space. The Dirac point will split in K-space into 2 wild points. That is almost what happens in tungsten ditelluride. Now, this is an inversion breaking wild semimetal, and if it were centrosymmetric, it could not be a wild semimetal. And in fact, what theory tells us happens in this one is that when those wild points merge, they also gap. So you're not left with a Dirac cone, you're left with no cone at all. And that's, unfortunately, the drawing on the left, it's a little hard to see that in drawing 5, but there's a gap there that you can't really see. So what Aaron Lindenberg's group at Stanford did in a beautiful experiment is they excited an interlayer shear mode phonon. This mode, if you drove it far enough, would render the material centrosymmetric. That happens at 12 picometers of displacement, and that would definitely have to destroy the wild points by changing the symmetry. That is a symmetry switch, which was the title of their paper. What's actually going on is a little more subtle because their calculations show that you don't have to get there to the centrosymmetric state to destroy the wild points. In fact, you only have to move 2.2 picometers. So you're still inversion breaking, but you've brought the wild points together in K-space and annihilated them. And you can see in their data, the data are the bottom curve in blue, that's the displacement of the atoms as a function of time, that they can do this. They drive this material well past 2.2 picometers, and it gets there and it comes back and it's reversible and periodic, and it does this all in just a few picoseconds. So this is really nice. The top curve is calculated. That's the K point separation, or the wild point separation in K-space calculated from those conditions. The only thing you might find unfortunate about this, and frankly, it's great work, but the energy scale is pretty small. You can't see these wild points in ARPES, and frankly, any sort of optical or transport probe you might want to do will also struggle a little because of this. Now, how about zirconium pentatelluride, which we've also heard about? This is an interesting material. It's poised very close to the transition between strong topological insulator, weak topological insulator. Right at that transition is a Dirac semimetal. That semimetal is called fine-tuned. It's not protected by crystal symmetry or by topology or anything. And this material is so close to the transition that little things, changing the pressure, changing the temperature, changing the growth conditions, can move you from one to the other. Also, so can coherent phonons. Theory has identified several different symmetry-preserving phonon modes that will move you from weak to strong TI periodically back and forth with the Dirac semimetal in the middle. And we've heard about some experimental work in exciting those phonon modes too. Now, these obviously, since they don't change the symmetry of the crystal, they're not changing whether that Dirac point is protected or not. What they're changing is the band inversion, and that's the red-blue color scheme that you see in the theoretical curves. There is the orbital character of the bands. Perhaps even more interesting, if you excite a symmetry-breaking phonon, it's predicted that you would be able to create wild nodes in this. Here, the energy scale is a little better than in tungsten ditelluride. It's still kind of small, but it's starting to look like something you could hope to get direct spectroscopic evidence for with some difficulty. The other thing, though, about this is zirconium pentatelluride is, as they say, sui generis. It's not much like anything else, which means that you could do all sorts of interesting physics in it, but it's hard to see how that physics would translate into other materials. Okay, so within this ecosystem of materials in which coherent phonons can control the gap, where is strontium manganese antimony 2? Well, there are a few nice things about it. We've got this Peierls mode phonon, which is very easy to excite and which modulates quite a large gap, at least theory says 200 MeV or so. This is similar to zirconium pentatelluride in the sense that the phonon is symmetry preserving. So what happens when that gap closes is not that the protection of the Dirac point changes, but rather we believe that the inversion changes. I would like to say that this was unambiguous in theory, but actually right now, all of the theory about this is at least mildly ambiguous. We're in the process of building a tight binding model that will help us do a better job of answering some questions like whether this crossing is topologically trivial or non-trivial, and what the invariant associated with it is. Other things we might want to know is, what about the other Peierls mode phonons? There is one, for instance, which is not mode 36, that will repair that square net. Theory seems to suggest that that Peierls mode, if you can excite it, won't restore the Dirac cones, which is mildly odd. Other things we might want to know are topological surface states. Do they change as the band crossing is broken and restored? Because those are the sorts of things that you could hope to see in ultrafast ARPES, and so they could even maybe be diagnostic of this change. Finally, let me point out that we do need to drive this phonon 52 picometers, at least in theory, to get this band closing. That's a long ways. It's not absurdly long. It is not outside the realm of what people can do, but it is still not in the realm that is easy. So what can I say about this? I can say that this means that we get to have a lot of fun trying. Now, you could say that's just making lemonade when life gives you lemons, but we're in science for the fun of it, right? When you drive phonons a long ways, interesting things can happen. So we get to try tricks like maybe a sequence of pulses will amplify mode 36 while suppressing the other modes. That might be nice. We might get to use nonlinear phononics tricks. One of them that's particularly cool is that if you excite an infrared mode to very high amplitude, you can sometimes use that, if you're lucky, to drive a Raman mode. In this case, that would be mode 36. And you can even drive it in a rectified way so it doesn't oscillate. And finally, let me just point out the bottom here. We're coming back to Aaron Lindenberg's work on tungsten ditelluride. That blue curve you haven't seen before. That's what happens when they try to drive the material all the way to the centrosymmetric state. It gets there, but in a weird way. It oscillates like 1.5 times, then it reluctantly gets there over the course of tens of picoseconds, and then it's metastable. It stays there for nanoseconds. So this is all mildly odd. None of it is captured in the simple potential energy landscape that's in their paper. What this points out is simply this. When you drive crystals far from equilibrium, they're going to do strange things. And some of those strange things could be interesting. We expect to find some interesting things on the way to trying to demonstrate this control of the Dirac node in strontium, manganese, antimony 2. So to kind of sum up what we still need to do, we need to drive this photon to high amplitude and measure the amplitude. That's going to be ultra-fast scattering. And then we need to actually see the gap, the band structure change. That will require ultra-fast ARPES. The data here aren't ours. They just are there to show that the time and energy resolution needed are within the realm of what is possible in experiment. Okay. So this is what it takes, of course, to demonstrate a coherent phonon-based control of a Dirac material. And this is going to be plenty of hard, fun work. So to sum up, I've shown you why we want to open a gap at the Dirac point with ultra-fast pulses. I've shown you that in strontium, manganese, antimony 2, we can excite a phonon mode that is supposed to do this for us. And I've talked about some of the future work, what we still want to learn, what we still need to establish in theory, and the experiments we need to do, which will be fun, but hard. So please wish us luck. Okay. Thank you.
So, okay, good. It's my great honor and pleasure. And today I want to tell you about longitudinal photocurrent, CPG, photogalvanic effect in chiral systems. And hopefully the gist of the talk is basically to convey the idea that this kind of longitudinal circular photogalvanic effect is actually a unique signature or measure of the geometrical chirality in the crystal or in the electronic system. So I structured this talk in a rather broad way. I want to first talk a little bit about how we look for these kind of materials, how we got from a chiral material, tantalum arsenide, to the chiral one. And then I'll talk about the photocurrent, and then go into the charge density wave systems. And before I further go, I want to say that this is a collective effort with many of my talented colleagues, first at Princeton at Professor Hassan's group, and then MIT at Professor Nugadic and Professor Halilo Hilalo's group. Okay, so basically one sentence introduction. Biosemimetal is a very interesting phase of matter with many predicted phenomena, but for a while, there was no experimental material realization. So theoretically, we know that we need to look for biosemimetals either in a non-central symmetric or magnetic material. And at Princeton, we actually tried a number of candidates, such as the perchloroiridate, and they turned out to be difficult to work with for a number of reasons. So we got stuck in terms of looking for a biosemimetal for a while. And then we figured that, why don't we not waiting for the theorists to tell us to look for a certain material, but look for material candidates ourselves. So then, based on that inspiration, and we were thinking, okay, so this is a pair of vowel cones, but if we zoom out, it's basically nothing but a crossing between two bands, right? So then, if we basically crudely classify, the electronic structure into these four kinds, then essentially the front three are all so-called charge balanced systems. And we want to look for a semi-metal, but maybe we can get some inspiration from even thinking about what is an insulator, right? So sodium chloride is one of the most primary insulators. Okay, so a band insulator, and let's imagine this kind of conceptual experiment where I adiabatically blow the crystal up, right? I increase the lattice constant to infinity. So then in that case, electrons cannot hop from one atom to the next one. So then basically I get a bunch of discrete energy levels, and the lowest unoccupied level will come from the cation. So in this case, sodium, and the highest occupied one will be chlorine. So the anion. And then the next question is, what is the meaning of the energy gap? Well, it turns out that in this case, basically, the meaning is basically how much energy penalty I would need to pay if I would want to force the sodium to take its one electron back to break the ionic bond. So in this case, we know that this energy penalty will be huge because of the giant electronegativity difference between the two elements. So now let's reduce the lattice constant back to the experimental level. Each of these levels becomes a band. So therefore, we have an insulator. In this case, there is another there's another energy scale that comes in, which is the width of the band. So that depends basically on the hopping amplitude. Now, in this case, because the EG is so big, so therefore, we get an insulator, right? So that gives us an inspiration. What if we look for another hypothetical material, still ionic, but in this case, the electronegativity difference is much smaller. So then what we would expect is this EG is much smaller in the atomic limit. Now, if we turn the system back to the experimental lattice constant so that these levels becomes bands, then they would naturally cross each other. So that gives us a semi-metal. So therefore, the first strategy we came up with was basically we need to look at non-central symmetric because we're shooting for bio-semimetals, and we want to charge balance the system, and we also want a small electronegativity difference. So then, therefore, we basically go to the crystallographic database and put in the non-central symmetric space group numbers, and we got many, many compounds. And then we basically look at them and figure out and come up with the ones that we believe are possibly semi-metals. And then we ask our theoretical collaborators to do detailed calculations only on those compounds. So it turned out that this was successful in around 2014. We and also a group in IOP, proposed this tantalum arsenide. And actually, we also proposed a number of other compounds using similar methodology. And we also used the RPES to demonstrate tantalum arsenide as the first bio-semimetal material. But we did not stop there because, as you can see, this is a nice semi-metal, but in terms of the Weyl points, there are 24 of them, many of them, and the Weyl points are quite close to each other in momentum space, meaning that the Fermi arcs will be short. So then, can we find a so-called ideal bio-semi-metal? So then we ask ourselves, okay, what is the best semi-metal that one has ever seen with the largest separation? It's graphene. But then when we think about graphene, we realize that graphene is actually not a full shell system because it's carbon. So it's basically half-filled pz orbitals with the sp2 bonds. So then why is it a semi-metal? Well, it turns out that if we have a half-filled system, but if we have 2 degrees of freedom, that would mean 2 bands. And if the 2 degrees of freedom, in this case, the AB sublattice, are related by a symmetry, and then these 2 bands cannot open up a gap, then you would have a semi-metal. So this would be a symmetry enforced semi-metal, in this case enforced by inversion symmetry. So then we thought, okay, let's have a half-filled 3D system, right? What is the simplest 2 degrees of freedom we can find? Spin up and spin down. So what is the symmetry that relates these two? Time reversal can relate up to down. So then, indeed, if we look at a spin orbit system with non-central symmetric, then we have these Cramer's degeneracies. And that actually, like a Rashba system, right? That we actually know for a very long time, much longer than even the original proposal, theoretical proposal of a Weil fermion. And a Cramer's degeneracy is nothing but basically a crossing between a spin up and a spin down band at the gamma point or any trim point. But so it's a Weil crossing, right? So then we ask ourselves a question: can a Cramer's degeneracy be a Weil point? So it turned out that this question is not entirely trivial. If we think about any non-central symmetric crystal with spin-orbit coupling, then if the system still has any mirror plane, then the gamma point will be sitting on this mirror plane. It will respect mirror symmetry. And the mirror symmetry will basically reflect a positive chirality to a negative chirality. In other words, on the mirror plane, there cannot be any Weil point. So that really gives us another inspiration that what if we further constrain, not only look at non-central symmetric, but also no inversion symmetry. Well, it turns out that this corresponds to a very interesting subset of non-central symmetric crystals that are called the chiral crystals. And in this kind of chiral crystals, your unit cell is basically like your hands or DNA molecules that has a well-defined geometrical chirality. And indeed, our theoretical investigation shows that in a chiral crystal, all the Cramer's degeneracies at the gamma point, at the M point, at all the Cramer's points are Weil points. So therefore, they have maximally separated Weil points as long as your Brillouin zone, basically. So within those chiral crystals, we found the so-called ideal Weil metal to be this rhodium silicide and cobalt silicide, which now we are quite familiar with, and they have two Weil points, and they're maximally separated, one at the zone center, one at the corner, with this very, very long Fermi arc. So at that time, we basically understood this as an ideal Weil metal, and we eventually, at that time, we didn't appreciate also the interesting photocurrent response, which is what I will talk about next. Okay, so then, the reason that we wanted to look at this photocurrent is that when we look at the RPES data, well, these are, for instance, two Weil points and two Weil cones, theoretically of opposite chirality, but from the RPES point of view, there's no way to tell, right? So then we figure that what if we interact with the Weil point with a light that also has a chirality, like a circular polarized light? That's why we came to the CPG, the circular photogalvanic effect. And indeed, if we look at a single Weil point, then with a circular polarized light, we only excite one side, not the other, because of the angular momentum conservation. And if we look at this, this gives us naturally a current because we have the photoexcited electrons moving to the right and holes moving to the left. But of course, there's an opposite Weil point which gives the opposite selection rule and therefore the opposite current. So the whole thing should cancel because in any materials, Weil points come in pairs with opposite chiralities, right? But so then how do we get a global response? And that's where, again, this kind of crystal symmetry, chiral or not chiral, will come into play. So I'm just, in this case, let's imagine that we have a Weil point with Weil metal with four Weil points that are situated like this. Now, if I send in a chiral light like this, then it will select certain hemisphere over the other, depending on the chirality of the Weil point, which is either green or blue in this case. And as you can see, the pink areas are what is allowed or what is selected by the chirality selection rule, and they add up to basically 0. But if I further consider the crystal symmetry, then for instance, in this particular case, when I consider the crystal symmetry, each of these pink hemisphere will be reduced into smaller areas, okay? And now if I look at these smaller areas, then they are still symmetric for A to minus A, but they become strongly asymmetric from B to minus B. And therefore, that basically tells us that, this gives us a global CPGE that is along the B direction with a light along the A direction, shooting along the A direction, right? So now if I consider a different kind of vowel submetal, where, as you can see, the vowel points are situated on the Kramers points, then again, the chirality selection rule gives me this. Now, if I further consider the crystal symmetry, then basically everything about the corner vowel points are gone, and everything about the center vowel point is still there. So that again gives me a finite response. And it turns out that these two basically corresponds to the situation in the tantalum arsenide and the rhodium silicide. And specifically in the tantalum arsenide, basically this additional selection rule based on the symmetry comes from the tilting of the vowel points, because the vowel points are sitting away from the Kramers degeneracy, so they are naturally all tilted. As you can see here, I schematically draw the 4 vowel points and their tilting direction. And you can basically, as you can see, then the tilting will basically, this is a bit more detail, it will basically generate this so-called polyblockade, and as a result, leading to the reduced areas of this smaller slice. So in other words, in tantalum arsenide, it is fairly complicated. Basically, all the vowel points will contribute, but all the vowel points will contribute a small fraction because of this additional tilting induced selection rule. But indeed, we and also other groups like Professor Kenberg and also Professor Dongsun, and also Professor Dmitry Yalowsky, we all found this CPG, and also they found the shift current response, and the CPG is indeed due to what I just explained. Okay, in tantalum arsenide. So now let's think about the other case, which is rhodium silicide. Now this is the chiral one. So what is unique about the chiral one is that now the crystal symmetry basically means that the positive and negative vowel points now can sit at different energies, right? So now if I have the positive vowel point at the Fermi level, but the negative vowel point very far away, then with this photon energy, as you can see, the negative vowel points are completely polyblocked. As a result, my entire photocurrent response will only come from the single, the positive vowel point at the zone center. And that's why, in the schematic I showed 2 slides ago, you can basically select only the center one, and all the corner ones are polyblocked. And another very interesting point about this is then, because you are only sort of studying a single vowel point, it turns out that the CPGE, and more specifically, the injection rate of the CPG becomes quantized. This is proposed by Professor Joe Moore and Adolfo and the colleagues. And basically, it turns out that this quantization directly measures the chirality, the chiral charge actually of the vowel point that is not blocked. So yeah, as you can see, this will be the situation. So that's basically what happens to chiral crystals. And in this case, basically the chirality, because of the chirality, basically the CPG would be the so-called longitudinal CPG, in the sense that the current direction will be either parallel or anti-parallel to the light propagation direction, basically depending on the crystal chirality. And indeed, we actually tried a little bit, and actually they actually calculated this quantization. This is, I believe, an initial effort by tight banding model, and you can see that the quantization is fairly nice. Maybe there is more complications when you do more detailed calculations, but anyways, we actually tried a little bit using this CW CO2 laser to measure the CPG, and indeed we found the longitudinal CPG as a result of the chirality. But in order to measure the quantization, we need to measure the injection rate, and very interesting experiments along those lines were done both in rhodium silicide and in cobalt silicide, using this terahertz emission, the ultra-fast CPG generation. And that was done in Professor Orenstein and also Professor Liang Wu's group, okay? Okay, so that's basically what I want to tell about the photocurrent response in these kind of metals. And finally, let me basically go to the charge density wave. So basically our motivation is that, okay, so we have this photocurrent and the photocurrent is essentially a nonlinear response. And in this case, in the longitudinal current, longitudinal CPG is uniquely sensitive to the crystal chirality or geometrical chirality of the system. So can we find basically a phase transition system where the system originally at high temperature is not chiral, but it goes through a phase transition where at low temperature, it becomes geometrically chiral. And indeed, we found that there is such a very interesting system, which is basically the charge density wave compound titanium diselenide. So this compound at the room temperature is inversion symmetric, and at about 200 Kelvin, it goes through a charge density wave. And the charge density wave Q vector, there are 3 equivalent ones that are pointing from gamma to the 3 L points like this. Now, and basically basically what's really what was interesting is that by the STM measurement, it was found that this charge density wave is actually chiral. So what does it mean by chiral is basically, we have these 3 equivalent directions that all has a charge density wave Q vector. And it turns out that the STM found that on the different planes, at each plane, there is a dominant direction where one of the 3 Q vectors has a larger charge density wave amplitude. And that dominating direction is basically rotating either clockwise or counterclockwise, as you go from one plane to the next plane. But of course, there was some controversy because people also point out that the STM is only surface sensitive. So you could, look at some terraces, different surfaces, but in any ways, it's very, very surface sensitive. So then we thought, why don't we look at this by the CPGE response, which is about 100 nanometers. So it's much thicker than STM per se. So then basically we'll just use this longitudinal photocurrent. So then we basically, fabricated this kind of 100 nanometer or so titanium diselenide samples, and we measured the photocurrent. So this is the CPG, this is the photocurrent response at high temperature. We didn't see any CPGE, and then we basically cool down below the CDW transition. We also didn't see much CPGE. So then we thought that maybe what really happened is that when we cool down, both of the chirality domains can emerge. And if we look at a fairly large light spot, then maybe they will cancel. So then what we did, this came as a surprise, is that let us cool down while shining the circularly polarized light. And what we were hoping is that this light shining can be just like you apply a small magnetic field and cool down to train a ferromagnet, right? Field cool. So then we do light cool. And indeed, when we cool now with left-handed circular polarized light, we see significant CPGE. And when we then warm up, we see that the CPGE vanishes. And then we repeat the measurement with the opposite chirality cooling, then we see that the signals were reversed. And we also basically measure this response, while slowly warming up, and we can see that this signal disappear specifically at a temperature above 170 Kelvin, which seems to be slightly lower than the charge density wave transition. And finally, we also collaborating with Professor Di Xiao, they provided us a somewhat phenomenological theory for this, what we call the optical induction or training. Basically, inside this free energy picture, then the question is that how do we tilt the double well, structure, right? So then it turns out that in the free energy, one can basically add this additional term that is proportional to the E cross E star dot product, the light propagating vector. And it turns out that this basically, as you can check that if you flip the light chirality, this also flips sign. So this is indeed that will give you opposite tilting if you change to from left to right. And then the coefficient, yeah, that's what I say here. So then it turns out that then there will be a coupling constant in front of this. And it turns out that this coupling constant is basically the chirality dependent light matter interaction constant that depends on the details of the electronic structure and all that. And very interestingly, we found that this coupling constant is interestingly proportional to the Barry curvature dipole in a chiral electronic system. So then we could basically calculate this coupling constant, and then that sort of explains on a, I would say, on a phenomenological level the chiral induction that we observed. Okay, that's all. So with that, I would like to thank both the groups at Princeton, Professor Hassan, and all our collaborators, and also Professor Nonlinear at MIT, and the group members, and also Professor Pablo and his group members. And the works that I talk about was done at either Princeton or MIT, and was funded by this funding agencies. Thank you.